Hello, everyone. Welcome back to Ask a Scientist Gaming, where we combine mediocre gameplay with expert science. I'm Ken Hansen, a professor in the Department of Chemistry and Biochemistry at Florida State University. I'm a photochemist/photophysicist. I shine light on molecules and materials and try to track what happens to that light energy and hopefully do something useful with it, whether it's making and breaking bonds, transferring energy, moving electrons for things like solar energy conversion, catalysis, or photomechanics. But more importantly, joining me today is Dr. Fernando Febres Cordero. Fernando, if you wouldn't mind introducing yourself.
Yes, I'm a physicist. I'm a theoretical particle physicist. I'm very interested in how elementary particles interact with each other, like studying the fundamental forces, let's say gravity, electromagnetism, and then the nuclear forces. I dedicate my life to basically extract information from quantum field theories and compare to data that is collected like at the Large Hadron Collider. Yes.
And what do you typically teach? What's your go-to classes?
So, well, right now I'm actually teaching a college physics introductory class. It's one of these very large classes with 700 students. It's not only me. We have 8 faculty members teaching this class. But when I have been teaching undergrad, it's been these both the algebra based and the one that is calculus based. And then I also have taught the thermal physics, which is about thermodynamics, and the statistical physics. And in graduate level, I have taught quantum field theory, which is one of our most developed frameworks to study elementary particles because it combines relativity with quantum mechanics. And that's very natural for me because it's the field in which I work. So yeah.
Nice. All right. Equally important, what game are we starting with?
So perhaps as I introduce a little bit myself, I should have said I'm not a great video game player. So I kind of like very simple games, and maybe we can start with Tetris, which is one of the simplest things.
It is.
But
also one of the most challenging.
Even this thing is actually scaring me. I usually play it in a keyboard.
Really? Instead of a controller? I apologize.
So, but I guess I will learn.
Yeah. Back and forth, down, and
exactly. Yeah,
all right. So go ahead. Start button is right there.
Okay.
There we go.
And then I guess
Have you played this version of Tetris?
I think I play whatever comes with like Linux distributions. Yes.
Yeah.
But they are all very similar. Yes, I remember when I was an undergrad student, we would do like tournaments on this. So
awesome.
What do? I just select
press start?
Press start. Okay.
That should be good. We'll start at 0.
Okay.
Because you haven't played with a controller before, so we're going to see how this unfolds.
Okay, so that's good. Up and down. So okay. I see.
Yeah, but
very good. Okay.
Tetris is an all-time classic. For those
that's
who are
right.
not familiar.
So it's pretty simple.
It is, but an outstanding game. Yeah, this was one of the earliest Nintendo games. One of the most popular, actually. All right, yeah, if it seems like we're panicked to set up there at the start, it's because we're trying to get an Oculus, or it's called a Meta Quest now, right? We're trying to get a Quest to work on stream, and we've never actually done it before, and I think we have it.
Yeah, it sort of works, surprisingly.
But we're going to start with Tetris just because that was a safe bet.
Exactly.
But
not tricking around things there.
Oh, man. Yeah, and remind me, after this game, I got to get a screenshot of us with Tetris in the background for the YouTube channel, because usually we do that before stream, but we were panicked and trying to set up for the Oculus. But I think it's going to work. I'm excited to see.
Yes, let's see. I mean, this is very easy, so... The story with the Oculus is that a friend actually gave it to me recently as a gift to me and my wife, and so we started playing with it. It's kind of quite cool, the technology.
You like it though? It's do you feel any like motion sickness?
Yeah, so actually I really like the things that are mixed reality, because basically you get a little bit less motion sickness. With the full virtual VR thing, I sometimes do feel a little bit dizzy. Yes, but yes, I think they have, as far as I understand, they have come a long way.
Yeah.
And nowadays these things work way better. Yeah. Meaning awesome. That people feel a little bit better with them, yes.
So Cuddle Puppy said you should play Tetris in VR where the blocks come at your face.
that might be cool.
You need like a tactic response when it hits you. All right, but you said you're not a gamer. It's been a while, other than playing with the Quest.
Yeah, that's right. Yeah, exactly. So when I was, as I said in the brief introduction, I really like the whole thing of computers and how do they work, and they actually have driven me quite a bit. At the beginning, when I was young, I really thought that I wanted to be like computer scientist or something like that. But eventually, so yes, I have always been interested, and in my work, this is rather important because everything we cannot live without computers, basically. Yes.
I mean, it's just so much data at this point.
Yes, not only that, the calculations we perform are so complex. So normally in theoretical physics, there is this thing that students first might say, okay, I want to avoid the computer because I want to do everything theoretically on the board, in the blackboard. But in the end, you really need the computer if you want to compete, right? I mean, if you want to be with what people are doing, because everything, no matter how theoretical or how experimental, because of data, as you were saying, you need to have control of the tools, right? For example, computer algebra systems, which is to do algebra on the computer, you have to be really good if you want to get to the point where you are doing a state-of-the-art type of calculations. Yes.
Yeah, that makes sense. You got a shout out from Cuddle Puppy. He says, "Not a gamer, yet his Tetris builds are better than any of your previous Tetris playing guests."
Yeah, I think this might be
mathematical mind, right? The organization.
Exactly, like how content. I remember, and this maybe I should have told you, but there was even like a 3D Tetris that I was once playing, and that was even like crazier. I mean, like trying to visualize the figures as they were coming.
Yeah, so I don't know if you're familiar with so Nintendo had Nintendo Entertainment System, like the first gaming console. They also released a Virtual Boy. I don't know if you've ever seen this, but it was like the original pseudo Oculus, where it was mounted on a table and you looked at it.
Oh wow!
And it had like different layers of screens.
Okay.
But it didn't sell well because people were getting sick playing it. But it had a version of that, Tetris in 3D.
Okay.
I have an emulator of it. Maybe we should try it, but
see how it goes.
Yeah, I don't know if we can control it. It's more of a call out of the previous Tetris guest.
Right.
All STEM specialists should realize their credibility is on the line when they play Tetris. No, that's why we do this stream, though, Cuddle Puppy. We are humanizing our guests. Like,
it's kind of...
Fernando's an expert in high-energy particle physics, but...
Yeah, that's right. This is really not a comfort zone.
Exactly. But that's part of the fun.
Yeah.
All right, speaking of which, I like to start every stream talking to my guest about, in particular, like, everyone thinks we have this destiny to be who we are, right? We all knew we were professors from day one, and that is not true for a majority of us. And so 6-year-old Fernando probably didn't envision himself, in the United States, hanging out playing video games, drinking and playing Tetris. So what was the path that led you to where you are today? What were the major milestones from 6-year-old you to now?
That's right. I mean, you mentioned like 6-year-old. I mean, that my family, my whole, not only my parents, but also like my grandparents, my family is all very like social sciences oriented, and my father is a lawyer. So me being a physicist was sort of a strange thing, but how did it all come around? So I think when I was like 6-year-old and a bit younger, I was really in love with music. So not a lot to do with physics, although of course the physics of music is actually rather interesting, right? And we actually are teaching it in the class I'm teaching at the moment. But yes, as time went by, I mean, of course, the music was like a passion. I started to, and it's interesting because the computer thing, I started to be fascinated by computers. In particular, I remember my father, who is a lawyer, he would pick up like these pocket calculators, and he wouldn't trust them. Which was kind of a funny thing for me, because I was like, well, if this thing is if people are using it, what is it that you are not trusting, right?
Yeah.
So then, but of course, I mean, putting a simple arithmetic equation in the calculator drew my attention, and I was like, how does this work? So that was the question I would ask myself when I was in primary school and perhaps through middle school. And this was in the 90s, so computers were very basic at that time. But I actually went to some classes, and they taught us some basics of using a terminal, because this was the time in which there was not really like a Windows manager.
You
right?
didn't have GUIs, right?
Correct, not GUIs and things like that. So you had to do things like by command. And I think everybody might have told me, okay, this, I mean, what are you gonna do with these sort of things? But then as time went by, the first that happened to me to attract me to science was, I guess, the lucky thing, which is that I had an amazing chemistry professor. I mean, you being chemistry, and this awesome. Is when I was in middle school. And the cool thing that she did was that she always tried, whatever we were trying to learn or trying to teach, she always tried to put it in like an open-ended type of question, right? Like trying to show us that science is not something that you read written in a book, right? Nature is an open book, and if you actually ask the right question and you try to find the right questions, then you can come up with everything that is written in the books. And so that started really to catch my attention. She encouraged me to actually participate in these science Olympics that I think they are also here in the US.
Yeah.
I mean, there are these international competitions, right?
Yeah.
And
yeah.
Yes, and so that was it. I really got into it. I was really good at crystallography. I mean, at doing crystals in the lab. And then I went to college thinking that I wanted to be a chemist. But as time went by, I realized that the things I liked the most were like the physical chemistry, like the thermodynamics, like the quantum chemistry. And then, okay, this was physics. Eventually, it was clear that I understand the difference between our works in chemistry and physics, but the things that I was more interested was really physics. And then I was lucky that in my college, I am not sure in the US, but in my college, you wouldn't choose like a major, but until very late. So I was able basically to effectively switch to physics, and within physics the thing that I liked the most was like theoretical physics. I was for a moment thinking that I would go do math, but then I stay with physics, because the cool thing of physics is that math is it's not easy, but it's simple in the sense that all problems are like close. I mean, it's like a tautology. Like if you prove a theorem, you basically show that two things are the same. In physics, you have this game, like you don't know what nature is, you don't know what that thing that is outside is.
You don't get the axioms.
Exactly,
right? Yeah.
And so sometimes you have to be guessing, and the math might be wrong a little bit. In fact, the sort of math that we do in quantum field theory is really odd. It's full of like divergences and all kinds of weird things that mathematicians are usually not comfortable with. Although I have to say there is some formulations that are very, very solid from the point of view of the mathematical axioms. But yes, so I don't know. It all drove me towards like theoretical physics. For a while, I was doing this thing that is called string theory. And I did my PhD in FSU. Yes. So
where's your undergrad?
In Venezuela.
Okay.
Back in Venezuela. I did my undergrad in Venezuela, which is usually like very formal. I mean, we have people that work in very formal size of the science. Maybe it's natural because when you are doing like very theoretical things, you just don't need like expensive labs.
Yeah.
But I was very lucky to come to FSU, because then I joined a group in which the theory was all about trying to describe experiments, and at that time it was the so-called Tevatron at the Fermilab in Chicago. And so, yes, since then I have been doing what I'm doing, and it's all very exciting. And yeah.
Out of curiosity, how did you find FSU of all the places you could have ended up?
Yes, correct. Actually, I was applying to several places. I think I had like a working offer from London Imperial College.
Oh wow.
Usually what happens in the UK is that doing graduate studies is rather expensive, and they don't offer you like a TA-ship or something like that. And so when I was talking about this with some professor in Venezuela, she told me, "Oh, I have collaborators at FSU. Huh. She's a condensed matter theorist, and she said, "Why don't you explore this university? I mean, because it might not have been in your radar, and indeed it wasn't." And it turns out then that another professor also in my department had done like nuclear physics and had got his PhD here.
Oh wow!
So I got to talk to him and learn about FSU. Then I sent my application and they accepted me. So I was very excited.
Yeah.
I came like very open-minded, meaning that a good thing in the US with graduate level classes is that you can basically choose whom to work with after you are like in the program.
Yeah, lab rotations.
Yeah, that's right.
Yeah.
And so that was very cool. I was able to talk to lots of people, and yes, long story short, I ended up here.
No, that's awesome.
Yes, and it was. I think I was very lucky. Yes, I always felt FSU was a very wonderful place. Tallahassee is a small town, so not many distractions. So it was a good place to do a PhD, I would say. Yes.
I'm going to say it's a small city.
Correct. It's a small city. That's right.
I grew up in a town of 1,600 people.
Yeah. Before coming to Tallahassee as a faculty member, many years after I had left, I was living in a small city, let's say, in Germany. 300,000 people, so similar to Tallahassee. But the funny thing is that in Germany, that was a big city. Yeah. Because in Germany, a lot of the places are like very small town, like 10,000 people. Yeah. But on the other hand, in Venezuela, I had lived in very big cities. So.
Which city were you in?
Originally from a city called Maracay, kind of 1 million people.
Wow.
But my undergrad I did in Caracas, which is like 6 million people.
Oh,
yeah.
Very big.
Yeah, very big.
No, very cool. All right, everyone, welcome to chat. Wolfgang, welcome back. Greetings. How's it going? It's going well. We are playing a little bit of Tetris while talking about Fernando's experience coming to the U.S., going to graduate school at Florida State University. Thank you for swinging by. So after FSU, you did a postdoc? Is that
yes,
right?
I was. So after I finished here, I got the chance to go to UCLA. Actually then I went back to Venezuela, in part yes, because I had a necessity to do it, but also because I was happy to do so. I always felt like I would be happy doing science in Venezuela, even though that is more challenging because there is not so many resources for scientific work. But I think there is a lot of people that would benefit from me being there and things like that.
Yeah.
But unfortunately, politics got very complicated in Venezuela, and eventually I decided to. I think
All right. That's a good pause, though. All right.
That's a good point.
So we should take a break there and. Tequila.
Oh my! I thought we were start with like a beer.
Yeah, we can start with the beer. I'll give you the selection first. So those are the 4 that we have.
Okay.
So Blue Moon, that's an extra IPA, another IPA, and this is the Super Pale Ale.
Maybe the IPA. Yes.
Yep, it's all yours.
Thank you.
All right. Yeah, we should definitely have that on the side, but we might as well pour the tequila. Do you want ice?
A little bit, maybe. Yes.
Yeah, that's fair.
Just to soften it.
Yeah, exactly. I'm excited. I like this Patron. I don't take a lot of opportunities to drink it, but when I have that opportunity, I will. So if you want to pour, it's all yours.
Excellent. So let's see.
I don't know. Have you had this before? Silver Patron?
I think I have. Yes.
Yeah. I like this one. It's a sippable tequila.
Silver. Yeah.
Exactly. I'll open the beer first. We'll open a little gently. So, Fernando, cheers. Thank you for joining me. Everyone, hopefully you have a drink in hand. Last week of classes. Let's celebrate on a Wednesday night.
Exactly.
Video gaming and drinking.
Might not be the best time for it, but...
I'm glad you said yes. I know it's been a back and forth on the emails, but I'm glad you joined. Because it
was a crazy day, but I'm happy to be here.
And it worked out. We got some beer, we got some tequila, we got some Tetris. So if you can press start and go back to the main menu, we're gonna do a screenshot quickly for the YouTube video. Oh, you can put your name in. You are immortalized until I close this program.
Fair. Yeah, so I said that everything sort of started with me being very interested in computers, and so the interesting thing is that nowadays I also am always like trying to learn. But the things that I like the most is like the very basic. So sometimes the very elaborate games I just don't. Yes. For example, I also love board games.
Yeah.
But the game that I like the most is like Go. Do you know Go?
Yes, Go.
So the simplicity of it and the complexity of the game. I mean, that's what I like.
Chess
so
is easier to solve than Go. I think start. Yep. All right. So I'm going to reset this so we get back to the title screen. So I'm just going to take a screenshot. This is for the YouTube video. So if you just look straight ahead and smile when Tetris shows up, I will screenshot a few times. There we go. All right. Give me a second. All right. One of those is going to look right. All right. Awesome. So go ahead and press start and we'll keep grinding through. Okay. Cuddle Puppy wants to know, Dr. Cordero, can I use you as a professional reference since you're a theoretical physicist and I'm theoretically a physicist? Classic Cuddle Puppy.
That's a good one. Yeah.
My favorite version of that joke is whenever somebody's giving a talk and they talk about their theoretical friends. They mean they're friends that are theorists, but that's right. They're real friends, I promise. They're not just theoretical. Thank you, Cuddle Puppy. All right, Wizak, we got a first-time chat. Wizak? I don't know how you'd pronounce that. W-Y-A-Z-A-K. Wyzak. Thank you for joining us. First time chat. If you're not following, you should click the follow button. We only stream every 2 weeks, so if you turn on notifications, you'll get a notification once every 2 weeks. Also, we'd like to see our numbers go up. Last month, we crossed 1,000 followers, which is kind of crazy for a science stream. There we go. Thank you for, it's not Wyzak, that's Sleeping Up, which is awesome. Thank you for following us again. We like to see our numbers go up. We're at 1,026 followers now, which is absolutely incredible. But anyway, Wyzak wants to know, what song do you think a platypus could play on a keyboard? So I hope this is an inside joke and not a random.
I don't know. Perhaps Bach D minor sonata.
So you mentioned music. Did you maintain playing music?
Oh yeah, I try. I think.
What's your go-to?
Mariana, my wife, she would say I played the violin for a long time.
Oh wow.
I was like in an orchestra for more than 11 years. And it was mainly classical music. But when I was like in high school, some friends, they had a rock band. And even though very different, they invited me to join them one day.
A little bit of bass?
No, actually, it was just to join them and see what they were doing.
Yeah.
The interesting thing was that, they had their nice instrument, but they didn't know much about like musical theory and things like that. So then I said, well, I think we can learn from each other. And so it was actually very fun. And so all of this ended up with me also playing the guitar.
Oh wow!
And by the way, with them, I learned a lot of things, not only like heavy metal because they were really like into heavy metal, but also like jazz and blues and all kinds of things. And then I started playing the guitar. So nowadays I still have my violin. Now they try to play something. Sometimes in Christmas, actually, I do play something.
Oh, that's fun.
Yeah, because we do like a Christmas Day, maybe we play some music, but mostly a guitar. And now I have recently finally acquired a guitar. Mariana, my wife, she gave it to me, and yes, so those are my sort of go-tos.
That's awesome.
Yeah.
They were questioning why you didn't get the Tetris earlier. You built up quite the mountain there. So how does it feel playing with the controller?
It's similar, yes. I mean, so the thing that happened in the keyboard is that you use just the arrows, right? So
yeah.
So I guess I just adapt. The good thing of the arrows is that I think I play with a single hand. So here I'm playing with the two hands, and it's a little bit different, but yes, it's okay. I think I did play with a Nintendo controller when I was a bit younger. Awesome. I didn't have one, but I think my friend had one. You know, at home I only had like this in television. Do you know what that is? Yes.
Television. Do I have an emulator for?
And a Coleco.
Coleco, yeah.
Coleco, exactly.
Do you remember which games you played?
Well, the one of them I told you, this Donkey Kong. It was in Coleco. What else? Yes, and then the Coleco, interestingly enough, had some sort of Atari attachment that you could put
Interesting.
into it, and then we also use it to play some Atari games. Yes.
So I do have ColecoVision. Here's the games list I have.
Wow.
So I have an emulator for that. We could give it a try if you want to do it.
Well, we can have a look, but I just don't know if I will actually recognize something.
Yeah.
I have to say these were my siblings' thing that I sometimes use.
Yeah, no, that's fair.
I think so I'm the youngest in my family, and I think they were. I might have been a bit young and yes, didn't let to play too much.
Yeah. Or they gave you the controller that didn't do anything.
Yeah, probably exactly something like that.
It's classic. All right, Misadventures in Astro, welcome back. Physicists unite. Howdy, friends. Howdy, everyone. Astrophysics, high energy particle physics. It's all the same physics.
Well, yeah, one thing that I was trying to say a little bit in when I wrote my presentation for the show was that lately I have been doing something exciting, which is that, as you can imagine, I have always been connected naturally in this type of research with experiments like the Large Hadron Collider and the tiny things of the universe, like the elementary particles, electrons, quarks, photons, gluons, WZ bosons, the Higgs boson, the top. So all of these are very tiny particles.
Yeah.
So, but the exciting thing perhaps that I wanted to highlight is that about 5 years ago, some people noticed that some features of gravitational interactions could also be described with this type of quantum field theories that I have mentioned a little bit before. And what that meant is that we could actually start making predictions for something really completely different to what I have been doing, which is like gravitational wave observatories. So there is this exciting experiment. One of the detectors is actually in Louisiana, not far away from here. The other one is in Washington State. So it's two detectors. They form an interferometer that is able to detect something called gravitational waves, which is the fact that the gravity can actually travel like a wave through space. And detecting this is very challenging. Einstein predicted this like more than 100 years ago. And only in 2015 this was actually measured. Not because people were not trying, but it's because it's very difficult. But okay, very different thing. Why? Because the type of things they detect there are like black holes that have the mass of like 30 solar masses. I mean, like you multiply the mass of the sun by 30, and that's the type of black hole they detect. And this is very different to a very tiny particle, right? But somehow I have been able to actually make some predictions for that type of experiment, and that's basically opening like a new line of research on gravity, which was not in my toolbox, let's say. So that has been very exciting, yes.
I mean, yeah, that's one of my favorite parts. It's just like how ubiquitous gravity is, and yet we can't tie it to quantum mechanics yet.
Yeah, correct. Let's say it's difficult, yes. It's very difficult. And by the way, this gravitational wave observatory, even though that I'm using quantum field theory, they measure purely classical information. The observables have nothing really to do with quantum mechanics. We just use quantum field theory as a let's say as a toolbox to extract the classical information. But who knows? I mean, you know, we might people might get creative. I mean, trying to investigate what the quantum nature of gravity is. I hope that maybe some of the young people listening will get very interested, and they might tell us what is it that we have missed through so many years of science in trying to understand gravity.
That's awesome. So catching up on a few comments, Cuddle Puppy says gravity is only ubiquitous until you learn Kung Fu, as well as people in the Matrix and Crouching Tiger, Hidden Dragon. Absolutely. Physics is abandoned, or we could also go with Fast and the Furious. Physics doesn't apply there either. Cuddle Puppy also said, Tocar la guitarra. First-year Spanish students are rejoicing at their vocabulary being sufficient for once. Exactly.
Very good. Like pizza. Italian.
Yeah, I don't know. How often do you get to use Spanish in Tallahassee?
Well, not that often as if you are in the south of Florida.
Yeah.
In the south of
Like
Florida,
Miami
I mean,
is-
yes, so many people speak Spanish. But yeah, there is some communities and people is interested. So yes, there's a few restaurants that we have with nice like Venezuelan food. And,
Oh, what's
yeah,
your
so,
favorite?
It's called Venebites. I actually it's a bit of a of a commercial, but yes, they are really good. And so in there you find people that from the community.
Venebites. Where's that?
It's in 3rd Street, I think,
3rd
not
Street.
far from Cool Beans. Rather close to Cool Beans, yes.
That's awesome.
Yeah, very
Venebites.
nice place. Yeah.
No, I like to get the, you have the Indian guest on, you ask, what's the best Indian restaurant, right?
That's right.
I honestly didn't know there's a Venezuelan
Yes,
restaurant in
and
town.
it's really good. It's more like a type of fast food from Venezuela called arepas, but they do a very good job. Yes.
That's awesome. I'll have to check it out.
Yeah.
All right, so going back to the LIGO experiment, this gravitational waves, I love the fact that they use an interferometer, which is a
that's right.
classic like physics experiment. And so
Correct.
this is how we dispelled the idea of an ether, right?
Yeah,
Early
that's
on.
right.
And so,
Yeah.
so can you explain to the audience an interferometer and how it works? I know it's hard to do it verbally, but
yes.
best attempt.
So, well, the one of the first thing we learn, well, light is a complicated thing, but one thing that we settled a while ago is that in certain regimes, light is a wave. And being a wave, it actually can interfere with itself. I mean, we have all seen like wave on like at a pond, right? And we see that there is these patterns of like constructive interference, meaning like where the waves are very active, and destructive interfere, where they actually sort of cancel each other. So in a laser interferometer, you actually exploit this property, right? That you can interfere, and sometimes, for example, by light traveling different distance, if you superimpose them, you can actually see spots of darkness and of brightness. And that basically tells you about what happened with the light when it was traveling around space. So that's the interferometer part. And as you said, it has been a tool that has been used for more than a century, right? I mean, this ether, this peeling was happening like late 19th century, right? So what is extremely amazing of these new interferometers is that they can resolve features in which are like 1 in 1,000 the width of a proton. So it's like 10 to the minus 18 meters. So it's a crazily small size. So by being able to measure these is that they can actually detect these very powerful events. By the way, they are very powerful because it's like two very big black holes colliding with each other or merging into each other. Luckily, this happens really far away, like 1.5 billion light years away from here. But they, being so powerful, we can actually even detect them at this level because we have these tools. Right? So that's more or less. I don't know if it's a good description, but
No, that's
my
perfect.
attempt.
And so for this particular interferometer, you said one was nearby and one's in Washington.
Yes.
So they use that distance. And what wavelength of light are they using? Or approximate range?
So the let me say two things. First, I think the lasers they have, I think it might be just visible range.
Oh, wow.
Perhaps UV, but the point is that they are actually just measuring tiny differences in the
between the
path
two.
that the light travels.
I see.
And even though that the very good question, that they have these two interferometers very far apart, they are not necessarily need each other for detecting some of these events. So what does this mean? They can each one see some of these mergers, but the problem is that the noise is so large that you might not trust the observation of a single of these objects, of these interferometers. So then, once they have a signal, they try to correlate it to another signal in the other detector, and that might give enough confidence to say, okay, this is actually a gravitational wave event.
And so you know the time between those signals, what it should be of
Correct.
gravitational wave.
So
an earthquake will have a very different
Correct, and an earthquake or something very local will not be seen in the other detector. That is right. On the other hand, more than just corroborating, because this gravitational wave also travel at the speed of light. You can also use the fact that these two things are very far away to sort of triangulate. Well, you cannot triangulate because you only have two detectors, but it turns out that now in Italy and in Japan, there is two more of these observatories. There is two more of these interferometers, such that they can actually triangulate. And when they detect one of these events, they can actually tell each other, "Hey, it looks like this happened in this area of the space of the sky." And then you can, for example, tell observatories like Hubble to look into the same direction and perhaps see some electromagnetic signals coming from the same event. So it's pretty exciting. All of this is happening as we speak, meaning that is getting ready, and in the next decade or so, much more of this will be happening.
So that's what is that called? Parallax? When they do that?
Correct.
It's two different sources and triangulating.
That's right.
That's really cool. Yes. That's not bad. You got up to 83 on this one. Way to go. You're happy?
Yeah. I think if I had the other controller, I might be a bit
with the keyboard.
But it's okay. I mean, it's fun. I mean, it's difficult to talk about science while playing the thing, and it's completely.
That's what makes it fun. And so we should probably do a prediction. So I modified these since you sent them. I truncated a lot for one. Yeah. I turned this one from a factoid into a prediction because I thought it was really fun. Is there anyone you want to start with? Anything you're particularly excited to ask the audience?
Yeah, we could start with an easy one. Perhaps something like this one.
That one right there. All right. We'll see if it's easy. How many particle physicists are in the audience? But yeah, if you want to start another game, I will get this going and I'll ask the audience.
Well, I did more than before.
Nice.
I can put F.
So 83 is your top so far. Yeah, and later versions of Tetris, they have it so if you push the up button, it automatically goes down.
In fact, I'm used to this.
That's the one.
So it's actually way better when you can just throw it down.
Yeah. So are you familiar with the speedrunning community of this game at all, or the record-setting community?
A little bit, basically because, as I said, when I was like an undergrad student, we would do a little bit of like tournaments of Tetris, and I wasn't in the top, but I had a friend that he was, and so he would play online some of these things, and I saw people playing, and it was really amazing. But I don't follow. I don't follow. I just know that this happens, and it's very amazing.
Well, it's in the last 5 years or so, there's been a major revolution where they've essentially broken the game. They don't lose anymore.
Oh, I see.
And the technique they use is with this controller right here. I don't know if you've ever heard about this, but they use a tapping technique where they put their thumb on the button and then they'll tap the back of the controller with their fingers. So you can get 4 controlled taps really quickly. And that's how they control positioning. And so it's not like I'm moving it to the position. It's like I know how many taps it would take and I hit those. And that's completely broken the game. Like people just don't lose anymore now.
So somebody came up with this, I guess, by playing too much.
It's like a classic arcade technique, and then somebody started doing it in Tetris, and it's completely broken the game. So now they get kill screens. Now they have to have modified versions.
I guess you also probably have some AI playing Tetris. And,
exactly.
Pretty good.
Exactly. All right, ladies and gentlemen, we're going to put up a prediction right now. Those of you not familiar with Twitch or the stream, predictions are usually on Twitch. They're video game related, where someone's like, will Fernando beat 83 levels in this particular round? But on Ask a Scientist Gaming, we ask you science questions. And so I have my guests do their homework. They come up with several questions they're going to ask you guys. And we're going to pop up that question right now. You're going to have 2 minutes to answer this. An easy one. You're going to have 2 minutes to answer this. You're on Ask a Scientist Gaming Honor Policy. You can't use Google or Chat GPT or whatever you might use. Use your knowledge of particle physics or, I don't know, Fernando's gameplay to make a decision about what the answer to this question is. We're going to pop it up right now. And so Feynman diagrams, a way to talk about, particle interactions made by Richard or introduced by Richard Feynman, now known as Feynman diagrams. The question is, how many particles can a photon couple to? So a photon being a particle of light, I don't know if particle of light, a packet of light.
That's a good description.
Packet of light, how many particles can a photon interact with according to Feynman diagrams? Is the answer 2 or 3? And if you don't know, just guess. It doesn't matter. These are imaginary internet points. This is just for pride. But yeah, click that predict button. Depending on your degree of confidence, you can bet more or less imaginary internet points.
Very good.
So I'll be curious how this one unfolds.
Yeah, and try to answer it. And there is a follow-up one that we should, if we can do it shortly after, it would be doable.
Yeah, no, we can.
Just because it's a nice comparison, and we can talk a bit more about the structure of these theories after people make their cases.
Yeah, I'm curious. I don't spend a lot of time with Feynman diagrams. I don't know if you saw the PowerPoint that I sent you, the summary slide.
You brought one of my some of my papers. Yes, that was very.
I was looking for images, right? And I had either like graphs or I had Feynman diagrams.
Right.
So
I remember once sharing one of my paper with one of my colleagues, experimental physicist, and he said, "Wow, you don't have a single plot in your." I said, "Well, yeah, that's right."
But we
are really interested in the plots, but I don't make them. I send the information to the experimentalists that are the ones that put things together. Yes.
All right, you guys have about 15, 20 seconds left to put in your predictions. Feynman diagram, how many particles can photons interact with? Put your guesses in there. There's nothing to do but try, even if you don't know the answer. Feel free to guess. Man, we got a 1-to-1 bet, but a high confidence in one of them. The high confidence bet is 3. All right, Fernando, what is the answer?
Okay, the answer is 2.
2.
So it's not 3. So a photon can couple to 2 charged particles, and let's say if we are just talking about electromagnetism, so then it is, for example, against an electron and a positron. The positron is the antiparticle of the electron, and yes, so it is a Feynman rule that has 3 particles, but the third is the photon itself, right?
I see.
So that's the idea.
So let's broadly introduce Feynman diagrams.
Correct.
So this is just a nice notation bookkeeping, and there's a set of rules that you follow.
Well, let me say, so historically, as you were saying, they were introduced by Richard Feynman, who was really a genius in any shape of the word that you might imagine it. One of the things that he was great at was to actually simplify very complex, perhaps analytic calculation, mathematical calculations for even the general public, right? And one thing that was happening when he was developing the theory of quantum fields, which is this sort of framework that is relativistic and quantum mechanical, is that he was describing things to people and he was doing these figures. And some of the leading scientists of the time were always asking, like, what are these pictures you are drawing? We don't understand what is it that is going on. So it turns out that he came up with a way of introducing all of this complicated math and algebra through some representations in which the figures, the lines, represent particles. I mean, like, the electron is a particle and you can make them in the Feynman diagram like a line, and it travels through space, and as it travels it actually finds other particles, and in the vertices of the little figures, it actually describes the way that they interact with each other. So when I say that the photon interacts with 2 other more, like an electron and a positron, it means that there is a point in the space where these 3 particles can find each other and interact, like kick each other. I mean, that's a good description. They can kick each other in these vertices, and this actually ends up describing a lot of the theories that we have for interactions of elementary.
So I'm going to detour from Tetris for a bit just to show you guys the Wikipedia page. There you guys can see the image of just an example Feynman diagram. Yes. And so in this case, it has an electron going in.
Correct.
Introduces a photon.
A photon is the blue thing, yes.
Yeah. And then Q bar is
anti-quark. It's a quark and anti-quark, yes. So I told you that there is the photon that couples, let's say, to the left with the electron and the positron, or to the quark with anything that has a charge. So the quarks also have charge. The quarks is what make up protons and neutrons. So
the interaction is the intercept of those.
Exactly. Okay. And by the way, it might look just like a picture, but the picture tells us a lot. Tells us exactly what is the math that describes the way in which this interaction occurs, and we can transform that picture into a very precise mathematical equation, let's say, and that's how we that's how we represent.
And so, does it matter the angle you draw them out, or just the intersection?
No, they don't. The only thing that matter are the topological properties of it. Meaning, like, if you can deform one figure into another, then they represent the same interaction. But it doesn't matter if you move the lines around. It doesn't tell you anything. Yes. In fact, in the end, you have to integrate. That is like adding over all possible configurations in which they appear if you are doing this in a space coordinates. So yes, yeah.
All right, well, congratulations, Sleeping Up. You got an 11-to-1 payout. They followed, they got their internet points, they gambled on the question, got a high payout. It is 2 particles.
Very good.
And so we're going to follow up with an additional question right now.
Which is very good.
Essentially the same question, but we're going to talk about different particles. All right, give me 1 second. I'm going to put up another 2 minutes. You guys should, if you're not following, click the follow button, get your 300 standard internet units. And even if you're not confident in the answer, it doesn't matter. These internet units are mostly pride-based. They can be used to make us take a drink. They can be used to unlock emotes or ask for a factoid. But really, they're useless outside of the stream. So you might as well make a prediction, make a guess, depending on how confident. Put your points in there. Maybe you get an 11-to-1 payout like Signing Up just did. Or Sleeping Up, sorry. All right, so we're going to essentially ask the same question in a Feynman diagram, but in this case, we want to know the number of particles that a gluon can couple to. And so how many intercepting points does it have on the Feynman diagram? Right. Is it 2 or is it 3? Or with additional 2 particles or with an additional 3 particles? And so click that predict button and just put your answers in there, however you're feeling about this particular question.
Yes. So, and this I said is good because in a sense, like you said, these figures describe the interactions, and so this number that people are going to answer is going to tell you a little bit about the different types of interaction. And by the way, we are talking about a gluon, and perhaps not everybody have heard what a gluon is, but a gluon is just another particle like the photons. The photons are associated to electromagnetism. The fact that the photons in the picture, in the Feynman diagram, coupled to the charge particle is like this thing that we know really well from electromagnetism. If you accelerate charges, like in a current, you produce electromagnetic waves, right? This we learned from 19th century physics, right? So this one that appears here, the gluon, is the same type of particle of interaction, but now describing a very different force that we call the strong nuclear force. Yes.
All right, so put your predictions in now. You guys have about 30 seconds. Just make a guess, click an answer, predict one way or the other. Does a gluon interact with 2 particles or 3 particles on the Feynman diagram? Put your predictions in there now. You're running out of time. Spectroctopus, welcome back, which is a spectacular name, by the way. Spectroctopus.
That's a good name.
You are a little bit late, Spectroctopus. The previous question was how many particles does a photon couple to, which might be more in your alley. But this time we're going with gluons, and so we're going to figure out the answer here. All right, Fernando, what is the answer? According to a Feynman diagram, how many particles does a gluon interact with?
Correct. So perhaps you could have guessed that is the other answer, right? In this case, it can go all the way to exactly. It can go all the way to 3, right? So let me just say, okay, 2 or 3. What does this make? Well, one thing that it highlights very briefly, if you want, is that nuclear forces are more complicated. But describing the fact that they couple with more particles, it implies a little bit of more complexity. But perhaps what is actually even more complex is that these other 3 particles are gluons themselves. I told you that the photons can couple to other charged particles like electrons and quarks. So the gluon can couple to itself in a vertex that has 4 gluons, and that's why one of them can couple to 3, right? And that feature that the gluons can interact with themselves, it creates some non-linearities that makes the whole theory of nuclear strong interactions way more complicated. By the way, it goes under the name of quantum chromodynamics. The same way that we say electromagnetism for strong forces is called quantum chromodynamics.
All right, so what is a gluon? That's just a G in this diagram?
Yeah, so the gluons are the things on the left on the top.
All right, we're going to go to the diagram. So G star in this case?
Yes, but in there you don't have any of the ones that I'm mentioning.
So this doesn't have the 4 in it.
Perhaps you can Google something like Feynman Diagrams jet production. Yes, and then they will pop up.
And so Q is quark, Q bar is anti-quark, is that right?
Correct.
And
yes.
then...
So the gluons also couple to quarks and antiquarks. They do not couple to electrons and positrons.
That is.
The electrons and positrons only interact with photons. Well, also with weak forces, but.
And yeah. So these rules were known in Feynman's time, or these have been refined?
So definitely he came up with the ones for electromagnetism. But during Feynman time, in the 70s, actually, Feynman was still active. Feynman passed away early in the 80s, maybe 84, I think. So the rules for quantum chromodynamics were also put together. So he got to know about them, and he was definitely one of the persons doing important work in QCD.
So Feynman passed away in 1988.
88, okay.
At the age of 70.
Maybe that had to be because he was part of this team that investigated the Columbia. No, what was the NASA the discovery. The discovery that NASA sent that crashed.
I'm not familiar.
Okay, I
82 lines, not bad.
Exactly, not bad. Yes. I have the word in Spanish, el transbordador.
The Challenger explosion?
The Challenger explosion.
Oh, he was part of the investigation. I didn't know that.
Yes, exactly. He was still active, and I think this happened like in 82 or 84, yes. Man. And he was a part of a team, and I think he even came up with this whole O-ring theory that actually in the end turned out to be correct.
So Challenger was 1986.
Exactly.
So yeah, it's towards the end of his life.
Yes.
But the engineers knew that, like they reported that to NASA ahead of time, right?
Probably they maybe had known, yes, but he was in the investigation afterwards. Yes.
I see. All right, how are you feeling about Tetris? We are 51 minutes in.
Okay.
So you've been playing this game for 50 minutes. You want to keep going, or do you want to try something else?
We can try the Pac-Man, yes, just to have something different.
Switch over to Pac-Man. All right, I'm going to transition to Talking Heads. I should give you a question to keep you busy while we're going to change to this one, actual arcade Pac-Man. Okay. But yeah, in the meantime, what's your favorite equation?
Oh, well, it's my favorite equation. Good question. So I think one of the very exciting one is definitely Schrödinger's equation. So which is at the core of quantum mechanics, right? Perhaps because it's the general operator-based Schrödinger equation has survived time and is still at the core of a lot of the quantum mechanics that we do. Is even in the relativistic side, and it's relatively simple. It's just what it implies is really weird. So sometimes I say quantum mechanics is not really a weird theory. It's actually rather clean, mathematically speaking. It's just that what it implies and the kind of things we learn from it is just completely unexpected and out of the classical world in which we live day to day, right? So definitely that one. More technically, because Schrödinger's equation is like 100 years old.
Yeah.
This year, exactly 100 years old. But more recently, there are certain relations in quantum field theory that I really love. There is one that it connects, actually the equation that brings up Feynman diagrams. So it's a good thing to bring up. With observables is one that I love. And it goes through something called the path integral. So it turns out that a path integral is an object that generates information about these theories. it has a very compact expression that is written in terms of an exponential of sums of Feynman diagrams. and that connects these complex theories to observables. And I live in between there. That's where awesome. I live. I try always to extract information from these theories. So that relation that writes the path integral as an exponential of the sum of the Feynman diagrams is one that I also really love. I think it goes under the name of, the path integral.
That's awesome.
Yeah.
So the most common, I'm going to get your opinion on this. The most common answer I get from theorists and mathematicians and some physicists is Euler's identity.
Oh, okay. That's the basics. Yeah. I try to think about this in like more connected to what I do. Yes.
Yeah.
But definitely.
That's one of those elegant, simple. Yeah. Yes. But you use that regularly, presumably.
Yeah, for sure. Yes. Yeah. I mean, quantum mechanics is naturally written in terms of complex numbers. By the way, a lot of people try to undo what I just said. I mean, like, are complex numbers really necessary? There is people doing a lot of work trying to see if you can just decouple, because people feel like complex numbers are weird. But I just don't find it in these ways. It's a very nice number field, and it just has all of the contents of things that we actually observe day to day, like phases and things like that. So it's very natural, and so definitely things like Euler equation is just beautiful. Yeah.
All right, before we dive into Pac-Man, take a sip of the tequila. Yep. So cheers, Fernando. Cheers, everyone. Hopefully you have a drink in hand. Spectroctopus, I'm looking at you. Last week of class, let's celebrate.
Before the exams.
Exactly, before the final next week. I got to work on it tomorrow.
We have to learn how to use these.
Yep. So all you need is this one, actually. Okay. It's just joystick based.
It's just to move.
Yeah. And I'm going to give you quarters. There you go.
Okay.
Whole bunch of quarters, whole bunch of credits.
What are the quarters?
It's just how this is actually an emulator for an arcade.
Okay.
We don't have sound out of this guy. Give me 1 second. I'm going to troubleshoot this. I apologize. I'm going to cut you off.
Okay.
Make sure we get some sound here. Should have given you a question. I did not.
E equal mc squared, I guess, is another one that yes, is very profound, even though simple. Yes, another nice equation.
So now we should. Let's try this again. All right. Sorry, our Meta Quest hijacked the audio is what I'm thinking. So
yeah, let's see what happens.
There we go. Now we got some sound. All right.
Oh, there you go.
Now you're getting some quarters. I love the sound effects. All right. All right. Spectroctopus has redeemed request a factoid. So they've spent their internet points for a factoid, but they've been very specific on their factoid. Spectroctopus, you could have just asked it as a question, but we'll take your internet points. I would like to redeem my factoid to be on the topic of whether Fernando thinks that renormalization of QED is fair. Fair in quotes. So explain that to the layman, why that's even of debate.
Somebody really know the quantum field theory.
This is one of my colleagues in chemistry, actually. So they're curious if we were inside.
Yeah, definitely. So it's completely fair. Yes. So it turns out that the issues with renormalization are all related about scales. And there is some physics that is just not accessible to certain experiments and observables that we study. And the thing is that it looks very odd, right? Because it looks like if you are throwing away infinities, and what does that mean, right? I mean, like, when you actually write down the renormalization of a quantum field theory, you realize that the only thing that it's doing is just removing some redundant degrees of freedom. So in quantum field theory is like any theory has some free parameters, right? And then you have to fit them. And you realize that there are certain ones that are just due to the fact that the fields are not observable, and these parameters appear, and you have to renormalize quotation mark, meaning like you have to set them to some values. Sorry, you don't have to set them. I was trying to eat the...
It was worth a try. A little bit of rage emote.
Yeah. Yeah. So then it turns out that you have to find certain observables that actually take away that those undefined parameters. And in the end, this is what people like Feynman and Schwinger realized, that those parameters were unphysical. If you compute them through perturbation theory in a theory in higher dimensions than 4, you realize that these things look like infinities, but those infinities are just not there. They can be absorbed into these unphysical parameters, and they just go away. But as I said, this is a theory about scales. What happens with these parameters to at a very high scale? The quantum field theory has the problem that it's never a fundamental theory. It always works in certain regime of energy, and out of that scope, you will have a problem. QED by itself have something that is called as the Landau pole, which is that at some very high energy, by way higher than the Planck scale, the theory just blows up. But we can actually very systematically make all kinds of predictions and be very precise about how the observables should look. And so these theories are helpful, and they have proven incredibly able to describe data. Even though that in the end, we really need something that doesn't have these trickeries. It's part of the trickeries that I was saying the quantum field theory has. Yeah. Yeah.
All right, you ready? We'll keep going. How you feeling about Pac-Man?
I am feeling like I'm doing really bad.
So did you play this on computer, or was this joystick based?
I think in the computer too. Yes. Maybe when I was a kid I did play with joystick. But in the computer I is where I have played more recently. Let's say. Oh, now I ate it.
Spectroctopus says, "What an incredible factoid! Thank you so much." So they appreciate your answer, which is fun.
Yes. And maybe let me just go a little bit deeper, because I was talking about gravity in theory of quantum fields. So one thing that I think one of the questions I have, I don't know if I should give it up.
No, I mean you can. It's
but
fine.
one of the questions I wrote for asking people is like, can we actually write down theory of quantum gravity? And in my answer I wrote like yes or no, of course, and it was a little bit of a catch. So the catch is that most of the people would have heard that there is no way of writing a theory of quantum gravity. But I like to describe this in the context of renormalizations as actually sort of the opposite. Because the point is that we can actually write theory for quantum field for gravity. It's just that we just can write way too many. So these theories are not well defined, because the amount of parameters, on physical parameters that you have to fit, it just grows and grows as you go more and more precise. And so if I tell you I have a theory that has 1 billion parameters, so that's sort of the opposite of a theory, right? Because it's just all of the predictivity of the theory goes away. Like, for example, I guess ChatGPT, what have shown is that, right? If you give me 1 trillion parameters, I can fit anything, right?
Yeah.
So the quantum theory of gravity has exactly that problem. You have to, the more precise you want to talk about things, the more parameters you have to fit, and so then they are not very predictive. So then, yes, that's an open question. We do not know how to make a nicely looking theory of gravity.
That was close.
You almost
got out of the weeds on that one.
I think maybe if I move a little bit, no, I shouldn't move. Maybe if I move the joystick.
Yeah, move the joystick wherever you want. Spectroctopus. It sounds like if you need an external member on a committee, Fernando's all in on it.
Yeah, I would be happy to be, yes. I actually enjoy very much being in committees outside of physics, because you learn. I mean, it's just sometimes very different things, and yes.
Exactly, and that's one of the things I like about Ask a Scientist gaming. I learn more from external colleagues, right? Like,
that's right.
And especially the social scientists, because I know nothing about that.
That's right.
You and I still talk a similar language despite being in different disciplines, but man, they're in a different world.
When you go there, it's very different, yes.
Yeah.
And I have been in some committees for social sciences.
Yeah.
It's always very interesting, and sometimes they have very advanced statistical methods and things like that.
mean, my bucket list item, I want to be on a like music theory.
Oh, that would be
Just-
very nice.
Just for fun, you know, just something.
And
way
I
out
think I
there.
would enjoy it very much because, as I was saying at the beginning, I studied music for a long time, so it would be a very nice exercise.
That would be fun. Yeah.
And FSU has some pretty nice musicians, right? I mean, the music school is amazing, right?
Yeah.
There's all of these festivals that they do. The Festival of New Music, I think it's every other year.
So I've been through physics. I've done condensed matter, astrophysics, and high energy particle physics.
Oh, nice.
Biology, engineering, but yeah, not anything beyond that. I guess I was on one in psychology, which is neurobiology related. Which
I am now in one in psychology. It's very interesting. Yes.
Interesting. What are they?
I think it's about memory and how we recall memories. It's starting, so it's I think the project just started.
That's fun.
So yeah, I don't recall right now.
So the question is, how did they find you? Is this somebody you knew?
Yes, somebody I knew that I knew. Yes, and I have had several friends in the psychology department. So then they sort of found me. Yes.
That's fun. All right. Cuddle Puppy, following up on Spectroctopus, I would like to redeem a factoid to be the number of and location of all bones in an octopi. They talked about him being spineless. Is that there was an exchange that happened earlier that I missed out on. Oh, man. Oh, knuckles cracking. That's where it was foundationally from. Knuckles cracking and cartilage. Pockets of air within cartilage. That's a good question. I think octopi have cartilage. They don't have knuckles.
Oh, okay. I can still try to.
Oh yeah, we have infinite quarters. Somebody can watch the YouTube video and figure out how much money Fernando has spent on this if it's a quarter for life. But did you do any arcade gaming back in the day?
A little bit. Yes, like with the big machines, you mean?
Yep.
Yeah, a little bit. I think I really like these sort of places when okay.
No,
was good.
GG's. Yep, there it is.
Come on.
We'll even give a Carl Sagan on that one. Well done.
Okay, I can start again. Yeah, so I was gonna say when they became a little bit more like because the arcades were the very basic, right? But when they became like a little bit more like simulation, like with this card and the flight simulators, I really like going to the places to play those. Yes.
So have you been to there's in Railroad Square Park? I don't know if you've been there before. There's a flippin' great pinball, which is like classic pinball and arcade, but there's also a VR studio there.
Okay.
I don't know if you've seen it, but
I have seen it, but I have not.
So my daughter did her like 9th birthday party there.
Okay.
And so
nice.
what they did is they had just like these 10-year-olds running around with VR headsets fighting zombies and stuff. But it was pretty fun. I didn't do it myself. The kids were dominating the space, but it's really nice. Big open area. You walk around. You can use the guns, and yeah. It's worth it checking out if you guys haven't. You should probably do like a group party there, maybe. I don't know. I'll have to figure it out.
You can do an Ask a Science test around it.
Yeah, exactly. I thought about that, partnering with them, because we've done it at the Challenger Center, actually.
Okay.
Me and David Collins, we streamed from we used the IMAX screen.
Okay.
And we had the video game on the IMAX screen, and we streamed from the back, which is pretty fun. And we have to do the planetarium at some point. That would be fun.
Yeah, planetarium is a lot of fun, yes.
And we've also streamed from the Mag Lab, but not from First Friday. I guess that has to be on the list. All right, we should put up another prediction because I mean we have a bunch of them. We've gotten 3 of them. Let's which one do you want to do? I'll wait for you to.
Yeah, let's see. I'll die very soon.
But yeah, if anyone has questions for Fernando, he's happy to talk about high energy particle physics, talking about how to correlate or how to relate, gravity from interactions.
Gravity,
yes. Yeah, particles. We're talking about
what are we looking for?
Yes, throw your questions in there. See, he cares about CERN. He cares about LIGO. He cares about all the detection systems. Misadventures is still around. I know you have something. What's fun is you kind of transcend. You're not. You're not exclusively particle physics because you care about the astro.
Yes, correct.
The big things as well.
Yeah. I mean, there is a difference between, I enjoy all kinds of physics. Of course, in the end, I think modern science and perhaps just being a normal person, you have to focus your efforts in some particular field, right? So what that means,
Get it? Oh,
it seems like I was safe.
perfect. Veteran.
Good.
Oh, totally worth it.
So I was gonna say that
Somebody should clip that. That's amazing.
That you have to choose your battles, right? So I like to hear about everything, right, and follow a little bit what things are going in all kinds of sciences. But in the end, yes, I focus very much on the type of things that I have been training for, and where you can actually make contributions, right? So in the end, I mean, the day-to-day on scientific work, right? I mean, this really well is like these tiny things, right? That you have like this long-term goal, right? And then you are getting towards it, and but every day is like these epsilons, right? And sometimes those epsilons are very exciting, right? So yeah. So you said that maybe we look at
incremental progress. Yeah. Which one do you want to do? What else should we?
So maybe that one like this, just to make it a little bit more phenomenological.
Yeah, that's fun. All right, I'm going to put up another prediction, and I will start the game for you right now.
And maybe next we could do this.
Yeah.
Although there is some.
Oh yeah, I did an over/under, so I just said less than or greater than. Yeah, sometimes for character count, I have to modify the outcome, unfortunately. All right. I'm going to pop up a question right now. If you're not following us, click the follow button. We love our numbers going up, but also you guys love standard internet units. Make us, take a drink, make us repeat a factoid, unlock an emote, whatever it might be. All right, we're popping up a prediction right now. Prediction, you click that button at the top of your chat right now that says predict, and we are asking you the science question, and Fernando is going to give you guys the answer after 2 minutes. But the question is, what are the number of electrons required to outweigh a top quark? So a top quark is definitely heavier than electron, but if you have enough electrons, they're going to weigh more. So if you put a quark on one side of a balance and the electrons on another, how many electrons do I need to add to outweigh the top quark? Top quark is the heaviest?
Is the heaviest non-elementary particle, that's right.
And so the question is it greater than 250,000 electrons or less than 250,000 electrons? Which is a fun order of magnitude question. Cuddle Puppy says 3.
Because of the gluons.
Exactly, gluons. The answers thus far have been 2 and 3, so not an unreasonable guess. So, Cuddle Puppy, feel free to say less than 250,000, which 3 is much less than 250,000.
That's right. This is a little bit highlighting the fact that so we have this theory called the Standard Model of Particle Physics, which is one of the most successful models that we have built as scientists. This was first written in the early 70s. And within it, there is all of these particles with all kinds of different masses. And this is highlighting a little bit that, yes.
All right, you guys have about 30 seconds left. Put your answers in. How many electrons to outweigh a top quark? And these numbers, these masses are known to like dozens of significant digits, right?
Particularly the electron, because the electron, you almost can put it like in a very precise balance. That's not how you do it. But the top quark is the heaviest, and it's known to 1 per mil, at the level of 1 per mil, and people are trying hard to even do better.
Yeah, that's amazing. All right, last ditch answers. All right, we have... Most people said greater than 250,000. What is the answer?
So then they got it right. I think the number is closer to 40,000. Yes.
Yeah, you put
exactly, 338,000. Yes. So it's a 5 order of magnitude, basically a bit more than that. And that's within the early version of the Standard Model from the 70s. This is the biggest gap between the masses of the different particles. Of course, we have the massless particles, like the photons.
Photon, yeah.
but the electron and the tops are the heavier one. Now, in the late 90s, and this is one of the big problems for the Standard Model, in the late 90s, we found that the neutrinos, those very funny particles, we can talk about them, they also have mass, and their masses are really tiny. We don't know how tiny. There's a lot of experimental efforts going on in Fermilab and in laboratories around the world to try to set this up. But it could be that they are even like 10 to the 5 times lighter than the electron.
Wow.
Yes, and this is sort of real new physics, meaning physics that goes beyond the standard model.
So is that still debated if a neutrino has mass?
No,
Or is
it's
that-
really well known because
known, okay.
the existence of the mass allows for the neutrino to switch flavors. Like an electron can become a muon. I mean, that's what we call as flipping flavors. I mean, one neutrino can change into a very different neutrino, and that's only because they have mass. And so that's the indirect way that we know that they have mass, but we have not been able to measure it directly.
I see.
Yes. So
So
then
we
we
know
only
it
have
has
like
mass. We just don't have an exact number.
we only have like limits. I think it's on the order of let me just think for a second. Like 6 order of magnitude below the electron. We know that has to be less than that.
Wow.
And this mainly come from cosmology, because if the neutrinos had mass, I mean, it would weigh on the universe as a whole. Yes, and so people actually, but there is plenty of experimental efforts now trying to pinpoint this more precisely. Yes.
That's really fun. All right. Congratulations, those of you that said greater than 250,000. Yes, 338,000 times.
Yeah. That's
And so
huge
that's
difference.
that's the heaviest and lightest like quantified mass difference. And that's
One example that I give, because sometimes these numbers are weird, but one elementary particle, top quark, it weighs as much as a gold atom. And the gold nucleus is rather complex, right? It has a lot of protons and neutrons. 183. I mean, you know better your periodic elements. So these elementary particles is as heavy as that. And then on the other side, you know that the electrons are really light, flying around, and they do all of the chemistry, right? Because they are light, they allow all of the chemistry, and the molecules and the interactions.
They get to tunnel and all sorts of fun stuff.
Correct. Yeah.
So remind me, a proton is made up of which quarks? I don't remember the pairs.
So there is some valence quarks, and there are 2 up quarks and 1 down. But in a sense, a proton is like a ball of fire of all types of quarks and antiquarks and gluons. But if you add over all of them, you get the valence, the ones that don't add up to 0. Let's say they don't annihilate, and those are the up, and down. And then the neutron is up, down, and down. Yes.
But you don't have any top quarks in neutrons?
No, you don't have any, because it's just too heavy. The uncertainty principle of Heisenberg doesn't allow you to have such a heavy thing inside the proton that is so light. Yes, and this even happened with a lighter cousin of the top quark that is called the bottom quark, top and bottom. Not very.
That's what I love about like a lot of physics names. They're either super or just like something super stupid. Yes. Like the God particle, the super Kamiokande collider.
Right. Like so the bottom is like 40 times lighter than the top, but even that, when you don't really find it as part of this ball of fire, the other quarks we have like up, down, strange, and charms. You do find them inside the proton. I mean, from the point of view of a wave function, I mean, it's like from quantum mechanical perspective, they can be found there. Yes.
That's very fun. All right, keep going on Pac-Man.
Yes.
All right, let's do it.
So is Pac-Man always? You see,
actually...
my question will show you how much I have played this. Is the layout always the same?
No, it changes.
Okay. As I go up to new levels.
And disclaimer: this is Mrs. Pac-Man. It actually behaves better on the emulator, so that's why we play it. But
okay,
she has the bow.
Yeah. I see that she has the bow. Nice.
But yeah, Mrs.
and also
Pac-Man.
the lips, right?
Yeah, exactly.
Because
and you might appreciate this, being a theoretician and also programming and computer related. A lot of these computer emulators, they take the hardware and recreate it in silicon. And the reason they do that is you have to make it true to the original arcade.
Exactly.
Right? So if you're going to speed run, if you're going to
So they emulate the hardware and then they put the same program.
Yep, exactly. And execute it on that simulated hardware.
Nice.
And it turns out to work really well for some of these.
Yeah,
and they're very meticulous.
That's amazing. I mean, one interesting problem that we have in particle physics is that So we have experiment that has been running for a long time, right? And so sometimes some of the predictions that we do for these experiments are rather complex, and they are encapsulated in programs, right? There is a lot of standard programs. And one problem we're having is that as time goes by, when we try to look at the programs that did some predictions for some old experiments, sometimes they just don't run in modern hardware or modern software. I mean, like the OS changed so much that you just are not able to do this. And so people are saying, okay, we should always have some sort of virtual machine that can be emulated for the future. And then the programs are poured in this virtual machine, hoping like 20 years from now, if we want to look back at some of the predictions that we did for an important experiment, we can actually do so, because sometimes we just find the software and we just cannot run it because the environments change so much, the programs become so complex depending on so many different libraries in Python and in C++ and in Fortran and in all types of languages. So yes, it's an interesting problem.
And so you're
not only for
about,
gaming.
and you're talking about like single bit errors can cascade into
correct
problems.
Sometimes that can be a problem. That's right. Yes. And we normally sample like lots. I mean, the predictions are done through a huge amount of sampling of parameter space and things like that. And so yes, even a single bit lost can make a big difference. Yes.
Man, that's
but it's yes, and there is people dedicated to this is very interesting. But also like
what?
I don't know what happened there. I was very lucky. They said, okay, let's spare Fernando.
Single bit.
But then Fernando ran into one of them directly.
It was close though. That was amazing.
Yes, so all of these kinds of things are very interesting, right? And I know that this is an issue, like people working on legacy kind of systems. Yes, yes. Now I guess that's one of the things where machine learning can thrive, right? Where AI system can thrive. I mean, if we train them early enough, they might remember all of these things and be able to actually do these runs in the future, right? We humans forget, but the machines don't, right? In a sense, right?
So speaking of legacy, like going on the spectrum from, we'll say, Fortran to Python, what's your favorite programming language?
Oh, well, I spent a good chunk of my life in C++.
C++.
One of the reasons why this is the case is because the object-oriented coding is just very natural for physics, because in a sense, some of the projects that I have been working on for the last few years, we actually, what we write down is really the physics. I mean, we don't really write code like in a way that you can perhaps recognize if you don't know the physics. I mean, we have a series of equations, and we make them look like that, exactly like that in the computer. So, and yes, object-oriented, it just helps a lot. And C++ is very efficient. Now, C++ is a type of language that I usually say that which is really good and it can be very efficient, but it's the easiest language to write really bad code. It's one of the languages in which you can really screw up so easily. And so it is unfortunately, even though that I'm happy with it, it's not an easy thing, for example, to get students working on. But by the way, I'm saying this, but sometimes I do get students that are way better, and I learn a lot from them. That they didn't spare me this time. So, but it's definitely a difficult language to get through. Yes.
And is that consistent across your community? That's the go-to, or? Is
a good question. So when I was a graduate student, it's like about 20 years ago, most of the software that was being built for Hadron Colliders was Fortran based. Perhaps not surprisingly. Not surprisingly, because it was sort of the choice for a long time in the 70s, and then there is a lot of inertia within the field. But sometime around that time, the CERN decided not to do any more support for programs written in Fortran.
Oh, wow.
And so what happens is that a lot of migration started to be done towards C++.
There was probably a lot of uproar to that decision.
Yeah, it was not an easy decision.
Yeah.
It was a huge, but of course they recognized that there was a need for a more modern. Although now Fortran also have versions that are Fortran 20, Fortran 2000, Fortran. I lost track, but definitely at that time they did the decision just because they wanted to break the inertia. And so then interestingly enough, that didn't stop people still to still use Fortran for a long time, and some of our typical software sometimes have kernels that are written in Fortran, which people just call indirectly. Sometimes they don't even know that these things are there.
Yeah.
Because they haven't done really well. But this is really a problem, because there is a point, perhaps the program working, it will keep working. But there is a point in which every software have to be rewritten for some reason, either because you need more capabilities, or because you realize that they were not, they were bugs, or that they were not as efficient as you could have wanted them to be, and then usually this creates a huge commotion, right? Because how long does it take to actually learn a legacy type of code and things like that? So I think it's a problem, and I'm always, so for example, I do not only do C++, but I try to keep up with the standards. So nowadays C++ is up to a standard, I don't know, 2023, I think is the latest standard. The packages I have built are so far in C++ 14 and 17. Why I have not switched, for example, to 20, which is more recent type of standards, is because not all of the compilers actually support all of the features. So I usually do the switch when the features actually become like available across many compilers. But this is very important just to keep up the sanity of the software, and to be able to bring up people, students, into latest type of development.
I mean, so those of us that aren't programmers, when you switch from 14 to 22, what changes? Like, what's the...
So it's always backwards compatible. So you can still keep using the older standards, but usually a lot of features are added that make your program more readable. So there is always a sort of effort to make programs readable, like you can use like more human type of language. I'm not talking about vibe coding or anything like that, but something like, I mean, if I have an electron and there is a function associated to it, let's call it a spinor, and there is a Feynman rule that is associated, I can really write in the code. I can really write in the code something like, okay, the electron with the spinor finds the photon, and you know, this is the way the code is written, right? And so internally, all of the complicated math is actually done, right? So things like this happen. One thing that has happened recently in C++, in some of the latest standards, is that they are actually trying to do them a little bit like Python, like very more modular, the existence of modules and things like that. So yes, these things happen, and I use a lot of templates within the code. I actually don't write code. I write what is called as meta code. This is code that is actually then instantiated in different types of classes and things like that. And so, for example, if I write like a physics operation, I can do it in either floating point or double floating point, or in rational numbers, or in integers, and this is all indirectly taken by the meta code. And so, and C++ has made this way more easily handled in the latest versions. So these sort of things happen, yes. And
yeah. All right, I think you made it to a new level, right?
Oh, very good. I should try again,
so,
yes.
yeah, if you want to keep going.
Yeah.
I'm going to run to the restroom briefly, but I should ask you a question before I do. Man, if you could completely change your research, what would you choose? Outside of physics, what domain would you go to?
Outside of physics, wow.
Yeah, no, and this could be music, this could be anything, right? What do you want to dive into?
Okay, very good. So let me think. So of course, yes. I mean, the thing is that in music, actually, when I was actually interested in music, one of the things that I liked was musicology, which is a little bit about learning about the theory of music and how different places and cultures have created rules for music. Right. This is all something I really like. But yes, if I was gonna go for music, probably I would try to do a little bit more like violin playing, or perhaps composition is something that I actually like throughout my life. A little bit making music. Yes. Not that, I mean, in principle, if you have an idea about a song or something, you can always just write it, right? You don't need to know a lot about theory to do so. But when you learn techniques, you actually become like more aware of possibilities, right? So yes, music would be one, but perhaps more on the scientific side, I think I would try to do a little bit of math. Even though this math, as I said a bit earlier, is like, you know, is always like relations that are just so well defined that in a sense you talk about the same thing in two different ways when you prove a theorem. I find it like so beautiful, very aesthetic, and there are things that I would be very interested to explore more deeply. There's some field in math that is called algebraic geometry, in which you study the characteristics of curves and polynomials and surfaces in multidimensional spaces. And there is some beautiful connections that you can find there, and that they have applicability over not only physics, but in many areas of research. So maybe math would be one. But those two things I just said are very, very naturally connected.
What was the first one?
Music, yes. Yeah. So music was the thing that I was saying a bit before.
Yeah, that's fun.
Chemistry, I really like chemistry, but it's a little bit like physics, right? I usually say not to say anything about chemists, but that in essence, what happens in chemistry is always physics, right? I mean, yes, I can say something. One science that I always found like so very challenging is biology.
Yeah.
That's a science that I always say, oh my God, I would be having a hard time, because biology always deal in complexity, right? So every system that you try to analyze there is so the thing that I like about physics and the little particles is that the key rules are all very simple. They build up to be very complex.
Yeah.
But when you go to a biological system, let's say ecology, which is, I know it's not the most exciting thing in biology nowadays, but if you go to ecology, it's like all of these interactions between so very complex things. I mean, like social sciences, I wouldn't even touch it, because if every subject of your study is different, I mean, I just don't know how to.
Yeah, the lines are much blurrier.
Exactly,
it's more discomforting.
I mean, whenever you do like a prediction, it's like very difficult to say what is the error, what is the impact. Reproducibility, which is known to be an issue for social sciences, is something that would drive me crazy, right? I mean, I would always, in physics and as in chemistry also, right? I think you always start by reproducing a bunch of previous results, before trying to push forward anything else, right?
Yeah, reproducibility is hard. I mean, even in chemistry, even in some of physics, right? That's But the blurrier it gets, the higher the abstraction.
That's
all right. We're at 9:30. Thank you all for joining us. Ask Scientists Gaming, mediocre gameplay, expert science. Our guest today is Fernando Febres Cordero. He's an expert in high energy particle physics, a theoretician that likes to model these behaviors and compare his models versus experimental data, like things that come out of CERN or the LIGO experiments, trying to, take the four forces and put them together in one magic equation that solves everything. Correct. That's the ultimate goal. And we're getting closer.
I'm finding if there are more, right? We know of 4 fundamental forces, but there might be more, right?
Do you think there's more?
Well, one of the biggest problems in our field right now is like what is dark matter and what is dark energy. So dark matter is this thing that we sort of indirectly through gravity in the universe, through astrophysical measurements, right? And also cosmological measurements. So it looks very much like some particle that we have missed. So of course, that could be associated to some other sector of particle physics that we don't know, and that there might be just natural other forces, that a fifth force or something, like we don't know, right? But perhaps more critical is like this issue of the universe expanding in an accelerated manner, right? So what is going on there? What is driving this? Sometimes the answer is like you might have like a cosmological constant in the Einstein equations, field equations. But I think it's a huge open question, right? It feels odd, like the universe is expanding because we don't have any force that could actually do that, right? Could be that is this cosmological concept, right? And right now there is a crisis in the cosmological models, and people are actually finding that this dark energy is not constant. I mean, it seems to change across the universe, and so definitely there are some very deep problems in theoretical physics. By the way, I work in the area where we are trying to break the standard model because in everything that we do on land in our labs, it just works so well, but when we look at the universe, the thing, it just doesn't fit. It just doesn't work. I mean, like these two things, we call them dark because we don't know. It's a parametrization of our ignorance. And so that's how we actually talk about these things. And so yes, yeah, there can be more forces lurking around. Yes.
All right. Misadventures in Astro. Cosmology is always in crisis if you read pop science news headlines.
That's right. That's right. I hope that it's not only like a clickbait thing.
Yeah.
Right?
Just add a constant. It'll all work out. Misadventures, thank you.
Add a parameter, right?
All right. Should we try the quest? Should we try VR for the first time on Ask a Scientist Gaming?
Yes.
All right.
I'm no expert, but yes. Okay.
I'm gonna transfer.
My good friend, which I think was here before, Nathan Kruk.
Nathan's been on. Scientific computing,
Scientific computing. So he really got me into this, and now that we actually.
Oh man, this is the first time we got this to work temporarily. I think we might have to log in again. It might have kicked us out, but we're gonna find out.
Log in again.
All right.
We can try again.
Oh no, you're good. We're still logged in. So if you just click connect. So press the meta button, go to camera. Sorry, you're just going to see,
I'll do it.
You're going to see Fernando look around randomly, but as soon as it connects to my computer and we can run it in browser, you guys will see it in real time.
So camera, right?
Yep. So go to camera, select cast, and select web. And if this works out, ladies and gentlemen, we are going to have... what's fun is you guys are going to get to see a augmented reality view of what Fernando sees. Oh, are you ready?
It's a little bit of this, the room in which we are, right? So.
All right, so let's go full screen. Should be a volume. We got rid of things. All right, ladies and gentlemen, there is what Fernando's looking at right now. Fernando, if you wouldn't mind looking at the room, they can actually see the streaming setup. So there's
there you are. There's a
signature board. You should look at the signature board if you guys haven't seen. So every guest that comes on, they sign the board right here. And so, Fernando has added the list of 90-some guests. And you guys can see.
It's kind of funny. I feel like in, I don't know, the Star Wars or the guy with the cover eyes.
All right, so we have the setup here, which is fun. Oh, you should look up there too. They haven't seen the, if you can see all the retro systems. We have everything from Nintendo to Famicom system to, and also the Ask a Scientist esports journey.
That's amazing, man. Where did you get it?
So FSU has an esports team, and I'm like pseudo honorary member because I bought a jersey. But anyway, what are we playing? What are we going for here?
So this is a role-playing game. I think I have played quite a bit, but usually with friends. So this is going to be like a random play. I don't know if you are looking at.
Yeah, we can see the random. So you click random.
And so it's a role-playing game, meaning that so I don't know. I have like a virtual board, and I can just move around the different.
Look at that.
Yeah. So I have. So I usually really like Sudoku, which is like a wizard, and it has a lot of powers that can make attacks from far away. Okay, so there is a dungeon. This is called a dungeon, and then basically what you have to do is to find. As we move around the field, it will start showing all kinds of monsters trying to attack us, and we have to basically field them and find a key, and with that key we will have to find a door to leave the dungeon.
Oh man,
so that's a little bit.
What I love is they get to see the VR aspect of this. They see the augmented reality and the secondary screen behind it. All right, while you're troubleshooting that, sleeping up wants to know how important are virtual particles? Well, first, what are virtual particles? And then second, how important are they?
Oh, very good. So the particles that we see in the description that we do in quantum field theory are the oscillation of vibrations of the field themselves. And these are oscillations that actually are able to travel across space-time, and then we see them asymptotically. What I hope that you see the board.
Yep, we can see the board. We see the top of it for sure. I think we see the view
but
you
then
see.
I have to bring it up. I wonder if there's a way that I can make it. Oh, okay. So like this, I think you see more.
Yeah.
Just search that.
Misadventures. We just left generations of gaming. Yeah, we jumped from like 1980s to
Exactly.
early 2020s. Absolutely. So cheers. Thank you for joining us.
So I hope
you guys
that
can
you
see my arm in the background and my beer.
Do you see that? So now the monsters are moving and they are doing all kinds of things to me.
And so this is like a turn-based system? How does this work?
Yes, exactly. So I have 3 players.
Yeah.
When it's my turn. Oh, do you see that gate over there that has 150 XP on top of it?
Yep.
So that's the gate I have to actually find my way through. But as I find my way through it, let me just get close.
Look at that.
Right. So there will be things like this. This is like a fountain of life. If I lost my life, I mean I can recover them there.
Oh, it's like a save point.
And then I can grab one of these monsters, and then the monsters, it will tell me all of the things that it can do, like the attacks, the movement, and they will try to basically kill me. So meanwhile I'm there, I'm that wizard there, and I have some cards. Let me see if I can show it.
Oh, look at that. Oh, with the other hand, look at that.
So then I can use these cards, and the firewall, for example, is something that will attack in a 3x3. So all of these thing is like a mesh, like a Cartesian mesh, and I can attack in a 3x3 sector, right? And if a healing potion will give me life and these sort of things. So it's that's a little bit it's a lot of fun because right now I have. So let me just go over there. This is one of my players. That wizard is called Zidoker. And then this other lady here is called Oana and is in my team. And then this Kai is like a ninja, and he's really good at killing monsters. But what I want to say is that right now I'm playing by myself. But normally when I play, for example, with like Nathan, so everybody, it can be in any place in the world and they are playing one of these guys, and it's like a team game. So it's a lot of fun.
That's awesome.
Yes.
So this is hosted through Meta? That's where your network is?
It's hosted through Meta, that's right. So for example, let me just do my first attack to this monster over here. I can come on top. And then this is
oh, there's the roll. Look at that.
I can grab it. I can do this. Oops, I don't know where to do it. Okay, so then the monster lost two lives, and then I can attack him again. I get to die again.
That is amazing.
And then that's it's not so different to some role play games that you play on the board. But of course it's kind of fun that you can interact remotely and these sort of things. What is it that I was saying before about science?
I have no idea. If you guys have any questions, throw those in chat while we play a little bit of Quest. What's the name of this game?
Demeo. Oh, and I killed the monster here, and so he goes over.
All right, the monsters are up.
Oh,
Demeo.
And then do you see that rat?
I have readied my spells.
I don't know if you see it in the...
Yeah, we see it.
Okay, that rat has like a key on top of it. That means that if I manage to kill that rat, I will get the key, and then I just need to go to the back over there to get out of this dungeon, and that would be like passing one level. Yes. Okay, so let's see. Let's see if I can get
open. Sorry, I got to change the name. Figure out the spelling of this game.
Demeo. D-E-M-E-O.
D-E-M-E-O. All right. D-E-M-E-O. Leap forward from Pac-Man. Demeo. There we go. All right, if you have questions for Fernando, he's happy to answer them while he plays this game, living in this augmented reality space. Does it distract you, the stuff going on in the background, or you not even notice?
No. It's okay. Okay, very good.
Man, that's got to be a crazy perspective
Okay, so
for this
now
game.
I'm gonna try to
That's fun.
kill the rat, although I don't think I'll manage to do it. Let's see. Okay, so this ninja is very, very powerful. He can really do some damage. Oh no, if I get that thing is like a miss.
What is that, a 12-sided die? What is it?
It's like how many sides? Maybe it's 12, yes?
It might be a
Just try again.
dodecahedron.
There you
Let's look at
go. Cancel.
it. 12, 1, 2, 3.
So let me just explain. Do you see those things, those like foully looking steps there? Like,
Yeah.
So that's a place you don't want to land on because you would basically get like sick.
And so when you do this with multiple people, you just take turns attacking?
Correct. Every person will have one of these characters, and then they
And then, so you presumably have a healer, you have a range, you have a
correct
different combat
different
types.
types of yes.
That's pretty fun. So have you played anything else on the Quest, or is this this
Yes,
your go-to?
we have played. I have played some other games. Perhaps things like see if I can attack the. See if I can. So let me just use one of just for fun. But this will not be very smart. So I'm gonna play a fireball, which maybe will show like a peak.
Oh.
Sabo, Markatash.
Nice.
That was the. Can get some money. So yes, there is all kinds of very cool things. Like there are some sporty things. Like you can do some workouts with them.
Have you tried?
Yes, I have tried, and they are actually fun.
Oh, that's fun.
And so let me see. I think now I should be able to get the key.
Oh, I found the question we were answering originally. How important are virtual particles? I think we answered that, didn't we?
No, I didn't get to it because virtual particles are let me just say two things. So in the there you go. So it's gone. So you see, I kill the rat, and then I get the key. So now I'm basically almost ready to leave the dungeon because I have the key unless they kill me. But I don't think so because these are the amount of life I have. Okay, very good.
I don't fear the undead.
Sorry that I'm concentrating here.
Yeah, I was gonna say you're more focused on this than Pac-Man.
Yeah.
Turn-based.
I ready
This
my
is, I think I can almost get
Miss Adventures wants to know if we can get VR NARC. Can you run NES games on the? I'm sure somebody's emulated something. But do you really want to dive in that world with clowns with knives and syringes thrown at you?
maybe not yet.
Oh man, but yeah, you saw the email. We're playing NARC. Probably we'll start at like 10:30ish. Bargain bin game for the NES. You're gonna have a great time. It's gonna be great. All right.
Okay.
Virtual particles.
Before I come back to the virtual particle, I'm gonna finish this level. So this one's easy actually, and I just come here. Oh no, it's locked. Defeat nearby.
Oh, you have to kill everyone before you can use the key. That's fun.
Who are the enemies that I haven't killed? I don't see them. Or maybe it's that guy.
How is this for you guys, the viewers? You're seeing like this game. You see a little bit of the board, kind of see a view, but you also see my video gaming room.
Yeah, exactly. Right is the best view. I actually can maybe make it even more nicely visible. Let me just
Oh,
do something here.
What's hard for Fernando is he can't see the microphone that's
Exactly,
in front
the
of him.
microphone is, you don't see it.
He's like punching the microphone right now.
Okay, I'll try to find where these people are. So maybe right. Cool. Oh, there is that little arrow there.
It's haptic feedback. I like that. So have you tried any of your, particle physics, computer programming within this VR space? I know in chemistry there's a lot of software developed for making 3D molecules, moving them around, seeing them. Have you?
No, I have not tried. People like to use them sometimes. So, for example, for visualization and things like that of data. And of course, one of the nice thing in principle, if you can survive it, meaning like if you can handle it, is that you can have like infinite screen space in these things, like 360 degree. Okay, so I'm just gonna win this. There you go. So then I won.
GG's. Congratulations.
Yes. Okay. So maybe I can stop a little bit now. So this is a new level. So yes. So the virtual particles is a very good question. So in the Feynman diagram we saw there was this E plus E minus that annihilated into each other into a photon, right? And then there was this quark anti-quark pair, right? So the particle in between the photon is called a virtual particle. Why? Because it turns out that photon is nothing like the classical like the photon that we would associate with the light that we have in this room, for example. Meaning the photon in the light that we like in this room, that we see in this room, is a massless particle. But if you compute the mass of that photon in that diagram we saw, is actually rather massive. So it's a virtual particle. It's not like a real one, but it's an actual oscillation of the field that comes from the quantum field theory that is associated to the same field, even though that is not really visible. So quantum field theory is just there's so many of these virtual particles that it complicates things. They have to be there because they are associated to the uncertainty principle in quantum mechanics. But one of the things that I do is systematically get rid of them as much as possible. There's a unitarity. It's called the unitarity method. We have developed it to be able to extract more information from quantum field theories that would otherwise be basically impossible. Some of the calculation we have performed, and I have a question about it in the set of questions we prepare, are really complicated, and they would be basically virtually impossible if all of these virtual particles were around. So we systematically get rid of them as much as we can. I have to choose some cards.
So
Yes.
sorry to interrupt. Can you guys hear the music at all? There is music playing. I don't know how to control the volume on this quest, but let me know if you guys can hear the. I don't know. It's like bards playing.
Yes, it's like a so
classic medieval music tone.
Yes, I'll buy some things. So let me just buy.
Ken drinking in the background. Okay, you guys can hear it. It's just going to be soft. Okay, good to know.
Regret getting that one.
All right, so we're at 9:51. Time is flying. One of the questions I insist on asking every single stream, because it's one of my favorites, is I've watched a lot of movies. And so one of the things I like to do while watching movies is see, did they get it right? Did they get it wrong? My expertise are science in general. There are some great examples. There are some terrible examples. For you watching a movie, is there any example? This could be particle physics, physics, science in general, things that people do right, TV shows, movies, things that people do wrong. What are the most memorable for you?
I think so it's very typical to find some discussions on quantum mechanics, on elementary particles, on forces and things like that in shows, right? I think most of them are okay. For example, the about black holes. This movie. Interstellar, yeah. I really love it. Of course, at the very end, there is this whole thing about like the connection and the love.
The most powerful force is love.
Yes, the most exactly.
Here's the thing you don't know, Fernando, is that the thing we're missing with dark matter is actually love.
Exactly.
And so if you would redo your models.
Exactly. What are you doing? You have to talk about
really
love.
Needs the revision.
Which, by the way, I'm okay. I mean, I know that it's like a way of telling a story, so I'm okay with it. I don't. Yes.
I get it.
But on the other hand, in fact, there were a lot of physicists associated with the making of this movie, and some of them are very famous. One of them actually won the Nobel Prize of Physics after the first gravitational wave events were found. And they did some of the simulations that happened in that movie, like for example with the wormhole and things like that. So it's serious people working on this. So definitely that was actually interesting. I love the movie, even though with the whole love thing.
And what upsets me the most is Anne Hathaway's character was so badass until it's like love is the answer. Like, come on.
Yeah, that's right.
Such horseshit. Cuddle Puppy says there needs to be a separate branch of physics called lovics. The love
Maybe that's what we have been missing, right? Like we need some of these too.
Here's my challenge to you, Fernando. You need to come up with a new theory and introduce a new constant, and that constant is the shape of a heart. No one needs Greek symbols. You need a heart.
That's funny.
And that heart needs to be incorporated in Feynman diagrams.
Exactly. But now, let me just say something. There is a show that is just so off, and it got so bad at the end.
Yeah.
It was a famous show called Dark in Netflix.
Yeah.
It was a German show. The first season was actually rather good, but the last season got into all kinds of nonsense, including the so-called Higgs field. So the Higgs field was some sort of bottle that would let them travel through space and time. I was so upset. I mean, I am kind of a funny. I don't have a lot of time to watch TV, but whenever I start something, even if it's bad, I try to finish. And it was a really difficult thing for me to finish watching this show because it was a whole lot of nonsense. Yes, so Dark would be one that I would explicitly quote, like getting everything very, very wrong.
So you wouldn't recommend, or you'd recommend because it's so bad it's good?
Well, I think the first season I would recommend. I think the last two you can give up with them. So no, not even for the fun of like watching something nonsensical. Yes.
That's fair. All right, so that gets it wrong. Any others that come to mind?
I love Gravity, the movie Gravity.
Oh.
Yes, I think they try to make it as close as possible to what you. Oh, I'm almost adding one of my characters over here. So you see Death in 3. I don't know if you see it, but
yeah, we see Death in 3.
So the sorcerer here, Sedokar, is dying, so I have to try to.
So in 3 turns you have to.
Exactly, in 3 turns I have to do something. The other friends that are very far away have to try to do something. I don't know. Let's see if sometimes there's like a way. Let's see if I go over here. Oh yes, this will save him. So I was lucky. That healed him.
So Gravity was space travel, if I remember correctly.
No, Gravity was not a space travel. It was actually just this person gravitating Earth, right?
Yeah,
and there was an accident. Sandra Bullock, yes. On top of that, I mean, she did great there. And I think it was also the male character was George Clooney, if I'm not wrong.
Yep.
What I love about that movie is that almost everything was really close to how it could happen. There were a couple of things. One of the things I remember is that there was an explosion in space, and the characters would hear like the and that didn't make any sense because it was an explosion far away. I mean, it was something that they were looking from the so that was of course really bad, but in general they did a really good job. So I really like that movie. And of course more movies like science fiction things like a classic like Contact. I love it. From the 90s, right? I don't know if you watched this movie.
Yeah, Jodie Foster. Yeah.
Jodie Foster, yes. Yep. And it's a story based from Carl Sagan.
Yeah.
Based on a book from him. So that was actually.
So what aspect about that speaks to you? Is it the scientist driven for knowledge? Is it the uncertainty, the chaos of introducing?
In that movie, so I was very young when I watched it. I was an undergrad student at the time on physics, and I think I went with my good friends till this day. We were as physics majors. So it was very exciting because, of course, it's a story about a contact from an alien civilization, right? It was very cool because, of course, Carl Sagan would always say the way
aliens would communicate would be through math. It's the only way, right? I mean, like, and it was about prime numbers. It was a little bit a story of about prime numbers, and so what was very cool is that in the end, the scientist that was the Judith Foster was realized in the end that there was a point in which our experiences cannot be proven in a sense. What we actually live, what we actually feel is non-scientific in a sense, right? Because it's not reproducible. I mean, what does it mean to reproduce what I have seen, right? And so there was a lot of this dichotomy with the connection with another alien that civilization that would be amazing to find. I mean, I think the search for alien life has changed recently in the last decade or so. We are not looking anymore for intelligent, but we are actually trying to detect like
bacteria
and vegetable
simple
life, right? We have these amazing the space telescopes that can do some of these things in exoplanets. I think that makes a lot of sense. But if this were to happen, of course, it would be transformational if we learn about new life elsewhere. So I like all of these things happening there, and the difficulty of doing science sometimes, right?
Yeah.
I always say that we scientists. I found the key. But of course, I'm surrounded. I mean, you see myself. All of these are monsters. So I have a spider over there. I have this monster, Elven Marauder. And he's really strong. I think I'm in trouble here. Oh, but I think I can sneak. So this is one of the powers of this. Yeah, so I think now they cannot see me. And then I can attack this at will.
So take-home message: love is the most important force in nature. Even in contact, because it's their data. Sorry, I don't want to spoil anything for anyone.
Okay, somehow I sneaked, but I was killed. I don't know, something happened there.
Ruthless.
Yes, very ruthless.
All right. So those any other ones come to mind?
Movie shows and things like that.
Yeah.
Which other movie I remember currently about science? Because it's about science, right? I guess I'm drawing a blank. I love The Shining. That's one of my preferred movies ever.
Have you read the book?
I haven't read the book.
Yeah.
But I do know a trivia fact. I think everybody died. Sorry, everybody.
No, we're gonna request a factoid. I want to hear trivia about The Shining.
Yes, exactly. Let me just see if I can turn this off for a second.
Ask a Scientist has redeemed. Request a factoid. So I spent
Let me just move this around because I haven't been able to drink anything in all of this time.
No, that's fair.
So here it is.
So how is it the VR, like when you try to grab something physically?
It's actually really amazingly good, and I understand that this last version of this headset it made a huge improvement in this sense.
So this is Oculus 3?
3S.
3S. Okay.
Yes, and I think this is like 2 years old by now. I'm sure they are gonna come up with something cooler, although they are really into the glasses nowadays.
Yeah.
Maybe do you mind if I just take them off for a second?
Yeah, no, exactly. You can take a break.
Yes, I can take a break and maybe play.
Curious what the camera's going to look at. There's my floor, ladies and gentlemen.
Yes. And that's it. That's
We'll
the
go to our
darkness of
talking
the floor. So what I was saying? Oh, yeah, the factor is you mentioned if I had read the book, which I haven't, which is of course very famous by Stephen King, right?
Yeah.
What I know, and maybe everybody knows, is that Stephen King did not like The Shining by Kubrick.
Yeah.
There were some changes that Kubrick did, like for example, it's not a axe what he uses in these final crazy scenes, but a chainsaw. So, but The Shining by Kubrick is a masterpiece of filming. Right?
Yeah. Does he still not like it, or was that just his
he
initial
just didn't
response?
like it, and he decided to make his own movie.
Oh my God.
And there is a Shining directed or produced by Stephen King, which is really bad.
I did not know that.
Yes, so that's my factoid or trivia.
I respect the author's original vision, but what translates well in text does not necessarily
Correct.
translate to a movie. So, yeah, he hated it, and Kubrick included a "Fu the King" Easter egg in the movie.
Oh my, I didn't know
interesting.
that.
What is the "Fu" Easter egg? Now I gotta
That
look it
was
up.
it. I will have to find it.
Shining.
I always remember a description of the Shining movie. Yes, the movie. That is something like this. If you haven't watched it, it is a movie in which you don't know what's going on really, but you do know that it's nothing good. It's not good.
Easter egg in it. Man, I don't know. I'd have to
You
find
have
the
to
right
find it,
sequence
yes,
of
yes.
keywords, but yeah. Yeah, so basically there's a scene with a car wreck, and the car in the wreck is a version from the novel.
Okay.
Oh,
I see.
interesting. That's a slight
Interesting.
slap in the face.
Nice.
Good
But
to know.
somehow I got into non-scientific movies. Yes,
I know,
with that.
but I love Stephen King. I love the translations to
Yeah.
movies, all of them, the best to the worst. What was the...
Well, I'm a big fan of Kubrick. I think all of his movies. I
Yeah.
just enjoy them so much. Yes.
But Stephen King translations, always great. Pet Cemetery, everything from like that to Maximum Overdrive to Shawshank Redemption, like, yeah.
Oh, yeah. I know the movie,
Wow.
but I don't know the book.
Misadventures
The
has
Shawshank
been
Redemption.
to the Stanley Hotel a few times.
Oh,
that would be fun, like
nice.
doing the tour and you see the
That would be
elevator and
something.
stuff.
Yes.
Man, see the hedge
Yeah,
maze.
yeah.
All right, it's 10 o'clock. What do you want to do? Do you want to keep doing that? Do you want to try something else? We talked about Donkey Kong. We could
I
bust
can
out some
try.
Coleco.
Yes,
Like,
I can try. I
take a
also
look?
told you that a long time ago I played this Prince of Persia, but
Prince
it
of
was a
Persia?
2D version.
Was it on Coleco or was that? Do you remember what it was?
It wasn't on some Windows. I mean, it's
Man, I don't know if I can bring that up.
Windows 98. But we can try Donkey Kong. I just it would be almost to play a new game for me, but it's something that I played a long time ago.
I mean,
Yes.
it's up to you. I have a list of the Coleco games. We can
We
try
can also
one just for
do-
fun, but
We can also do again maybe some other one of the things I did. Yes.
I mean, we could do Donkey Kong on arcade. It's
Okay.
probably the
Let's
easiest
try.
one if
Yes.
you want to do that.
Yeah, let's
All
do
right. Let's translate this.
Oh, by the way, there is a show which I really like. Is of course science fiction, and again, aliens are involved, which is the three-body problem.
Yeah.
That is really something, and I'm hoping that they release the new season sometime soon.
So, have you read the book of Three Body?
No, I haven't, but I have been told that I have to do it. That it's really different because it's like more Asian version of the whole thing.
It's hard. You can tell it's translated
Yeah.
text and it doesn't necessarily translate directly, but I mean,
yeah.
it's
But the whole game of trying to guess that this was a chaotic problem in a faraway
fun.
solar.
and I love they have like
A star
who was-
system.
Who was hanging out? They had like Newton with
Oh yeah, Newton, and then there is Copernicus, and then there is like who else was there? I don't remember who was the other scientist that they were.
but they were
Maybe, I
just
don't know.
like petty and
Oh
petulant.
yes,
and-
exactly. So
Yeah.
this is the one, but really, I will have a hard time doing this. Okay.
So let me get you quarters. All right. Hopefully you guys can hear that. Tell me if the volume's too loud or too quiet.
I think it was like I had to save. Exactly.
So this is the one you've played.
Yeah,
Not necessarily
I
on the
think
arcade,
so.
but
Not
this-
this one. Yes, but yes, there was the King Kong or Donkey Kong, and then I have to save the lady up there.
All right. We should pop up another prediction. Which one do you want to do?
So the computer one.
All right, let's do this. So Fernando does a lot of calculations. He does simulations, and that requires computational power to actually do these
Yes.
calculations. And so we're going to pop up a question right now related to that, in particular, the number of cycles required in the calculations. And this one's, it's a bit unfair because you don't know what calculation he just did. It
Exactly.
could have been 2 plus 2, but,
But
let's say-
let me tell you, so it's a state of the art. Is some of the most complex things that have been done in my field.
All right. So it is a very complex calculation. And so we're going to put up a prediction right now. And the question is, what are the number of computer cycles in Fernando's most recent calculation?
By the way, that's a weird phrasing, but it's basically like simple operations in the computer, right? By cycle, that's what I mean. Right? So if you do a 2 plus 2 in your calculator, that probably takes
few cycles. I mean, like 2 or 3 cycles to actually get it through.
So, okay, if 2 plus 2 takes a few cycles, how many cycles does Fernando's most recent calculation take? Click the predict button right now. Does it take less than 10 to the 15th or greater than 10 to the 15th? 10 to the 15th meaning 1 with 15 zeros behind it. Is it more or less than that in terms of the number of cycles he has to do this calculation? Can you give more context in this calculation?
So yes, I can say a bit more. So this is one of the calculations that I perform for black holes, and it is a very challenging quantum field theory. And what that means is that to extract the information, you really
So it's not responding at all?
It's not responding. So that's why
Give me a second.
trying to.
All right, I'm gonna assign some hotkeys here.
So in this calculation, what we were very interested in it was to pinpoint the information about how the black holes were spinning. So how they were spinning when they were interacting to produce these gravitational waves. And because of that, these theories are just way more challenging than anything we do in particle physics. Yeah, so it's difficult to guess, but maybe you can see if it's. You can I will give you a more sense of what it means 10 to the 15 a bit after you answer. Yeah.
All right, player 1 button. So let's do the jump button. Sorry, I'm programming keys right now, so we're gonna get these in. That should be good. That should be enough. Let's see if this works. All right, 5. Let's put some quarters in. 1. So go ahead and push that. Try the jump button as A.
Jump is A. Okay.
Yep. Let's see if this works. I'm optimistic. Cuddle Puppy says 3 cycles.
3 cycles.
which is less than 10 to the minus 15.
Good.
All right, so Fernando, what is the answer? How many number of cycles did your last calculation?
So it was less than 10 to the 15. So
Less?
you see, wait. Yes, I don't know if I'm doing it wrong. So
No, it might be.
so if I keep it.
Why is that not working?
Yeah.
Let me try this again. All right, Fernando, your answer is less than 10 to the
less, but not much less. So it was 10 to the 14. So what does this mean? If you transform this into time, computer time running in your laptop, it might be something like 25,000 hours. So if you were to run it in your laptop, probably, and your laptop is maybe not the fastest CPU we have. I mean, it will take I don't know, more than 100 years running. But of course, we don't do this. These calculations in normal laptops. We do this in highly parallelized supercomputers. I was using in particular one that is located in Berkeley. It's called, the name of this machine is Perlmutter. You can find it. It's one of the top 500 computers in the world. And in the end, we are actually able to do this calculation just in 9 hours running in like 200. There you go. There you go. Oh, there you go. So now I can jump.
Ooh, veteran. Off to a good start. Well done, sir. All right, do you need more?
Yeah, I can get a bit more. Yes.
All right, let's all right, ladies and gentlemen, we're drinking Silver Patron, so we're going to take another one of these. Just because it's fun.
I was saying that this calculation took like 9 hours, running in 200 nodes of CPU, but this is because each one of them have like 256 cores of calculation power. So, oops. Surprisingly, I managed to go 3 levels. I mean, I do remember this game, but I really haven't played it in like 30 years. So it's a long time. But on the other hand, my question was put like larger because people that do calculations, for example, in numerical general relativity, they can spend way larger than those amount of computer time, like 10 to the 18, for example. I thought I had avoided it. So also, if I was doing like, for example, simulations of low energy quantum chromodynamics, I would also use a lot more of. This question also came with a follow-up question, like, okay, if we use all of this computer power, how long does it take to actually report the results? And it's actually not so much. Maybe you want to put the question or.
So I mean, you could just.
Okay,
use
I
that
can
as a
add it.
factor.
Yes.
Yeah.
The factor is that we actually reported this in like 8 pages.
That's
It's
crazy.
perhaps yes,
All
exactly.
the necessary information.
All the necessary information actually just go into relatively compact expressions. One of the things that our field is trying to do is try to see if there are ways to actually somehow lift this information from way simpler calculations. But we have actually done a lot in that direction, and even with that, we still need lots of computer power. Yes. There comes a point in which complexity is unavoidable. But yes, I mean, we are always after clever ideas and people finding hidden structures within the field theories that we work in. So yeah, so if you are a prospective grad student, I will be happy to chat with you. Also, by the way, I have had a lot of undergrad students working with me. So I think by now it's like 11 of them.
Wow.
So if you are also doing like undergrad studies, I'll be happy to sometimes talk to you. Yes.
Anyone's interested,
There is
send
all kinds
Fernando
of,
an email.
yes, exactly.
Cuddle Puppy says, so you're the reason why PC parts in my electrical bill are so expensive. I mean, so do you have to pay for
Actually,
PC time?
the opposite, because using so much of this brings the prices down of these PCs. I mean, one of the reasons why some of the PCs that we have nowadays are so powerful and relatively cheap is because we use a lot of them. Yes. Yeah, I'm not sure. Of course, you have to make a more detailed analysis to see if.
So do you write computer time into your grants, or do you? How does that work? How is that allocated?
Good question. We have to write projects that are for computer time. So independently of the grants that we have,
We got this late. Oh!
Almost there. So yes, one of my funding agencies is the Department of Energy, and they have a lot of supercomputers, and so I get access to them after I write a grant that explains what is the usage that I'm going to give. Interestingly enough, they want to see that you are not wasting their resources.
And so in that case, it's not a full proposal. It's not like personnel and stuff. It's just instrument or
It's just for the
computational
instrument,
power.
but you have to show that you have prepared your codes to run in these machines. It's not like, okay, I wrote this in my afternoon and it's ready to be run. I need 1 million CPU hours. It's not the way it works. Yes, you have to really give a sense of your efforts to make this very parallelizable and efficient, and then they will give you the time.
And so you have to propose its efficiency, or somebody like looks into it.
So
And
sometimes they might actually want you to show the preparation that you have, like the scaling properties of your code. You might say, I need 1 million points. Well, what can you do with 100,000, right? And so then you show the output that you get from the simpler runs.
I see.
Yes. It's actually a whole interesting thing. Nowadays, these machines are very robust. But I started using some supercomputers in the 2000s. And I remember once actually bringing down one because maybe I made a mistake. I mean, but
You brought down one.
yes, exactly. So that was not a good thing. I think the first time I pressed a button and I asked for 50,000 computers, that was a very exciting time. And that was not the time I broke something.
Crashed it.
Yes, I didn't crash that one because I had got them slowly. But nowadays they are very robust. You cannot break them. I mean, they will detect that you are doing something wrong and then they kill your
Wow.
event very quickly. But also I have learned. I mean, I was very young and.
But when you crashed it, there was a bunch of people running on the same computer on different cores, and you crashed everybody's.
One of the problems is that at that time, nowadays if you kill like a node, so these machines are built up of hundreds of thousands of nodes. If you create one, the system is robust enough to just realize that and reboot it and bring it back later on. But at the time, I mean, it was early supercomputers, and so I think the scheduling system would get confused sometimes when there was like a hole and something happened. It's not like the whole machine went down, but I did have some impact, and I got contacted. Hey, what were you doing? You
got an angry email.
Exactly. Why this grad student doesn't know what he's doing.
It happens.
Yeah, it happens. I try to every time I work with early career scientists, I try to tell them, I mean, you should not get scared. I mean, you should get exposed. You try to do your best. It's not like you go blindly to do things, right?
Yeah.
But it's very important that people try and experiment with these things.
Yeah.
Because otherwise there's no real other way to learn about it. Yeah.
And I tell my students that every time, like, you try your best not to make mistakes. You're still going to make mistakes, but only make them once.
Exactly.
Learn from those. And
Learn
don't
from
do it
those.
again.
Yes,
Yeah.
exactly. Twice the same mistake is bad, and 3 is really terrible.
Oh,
Yes,
man.
you definitely have to learn from it, and it's a process. And
I mean, so is that the we have some canned questions for the stream, and usually it's like, what's the worst mistake you've seen? And it's usually like breaking a massive piece of glassware. But for you, is crashing the system, is that your biggest?
yeah, well, yes, it was it was not like a terrible thing. But no, I would not say that was my worst mistake. So, you know, in science, you have to always be very, perhaps, open to the fact that sometimes things don't work out, and being honest is really important, right? I mean, so there was a very important article that I published with a relatively large collaboration. We were like 6 or 7 theorists, and this is a very large community for theorists. We usually theories papers are like 1 or 2 co-authors, perhaps 3. But this was like a large effort, and this was also a computer problem. We were computing for the first time a whole new class of processes that we could pinpoint and describe very precisely. And there was this tiny bit, we were trying to be very careful in cross-checking each other, but there was this tiny bit that I was the only one who computed it. And then the paper went out before publication, by the way, because in high energy physics, we do a lot of preprints. That means publications that appear before they go into the journal. I don't know if you do this.
Sometimes, yeah. We have like Chem Archive. Yeah. It's much more common in math than physics.
Exactly. So before publication, we realized that this little bit that I had computed, there had been a very tricky computer bug. And it was really something that I was able to pinpoint and go very deep. And I could blame it into a tool that we were using, external tool. But it was a mistake indeed. And we found it before publication, and we were able to correct it before publication. So we didn't have to do like a...
So you found it, or a reviewer found it?
I found it.
Wow.
I found it myself, because one cool thing about... I say that science is like a little bit like paranoid.
Yeah.
The moment you learn something, you move on. Once you understand something, you move on to the next level. So while I was doing this, I was preparing for the next calculation, and the thing that I did first was to cross-check what I had done before. So it's always good to reproduce. And when I was doing this, I was looking at this tiny effort, and it was very funny because I caught it, and then we fixed it, and then we posted it as a preprint while the reviewers were looking at it. And so, but we were right in a conference, in a very important conference in our field. And when I was presenting results there, I found the problem, and I said about it. And right after my talk, there was some competition team that were going to show that we had made a mistake. but luckily I had just said, okay, we fix it. It was, let's say, I mean, it's science. I mean, you have to be open that mistake can also always happen, and this is very complex, and you cross-check yourself, and there can always be like a return to say, okay, that thing was not incorrect. But it was good that we had actually presented right before somebody else said,
That's awesome.
hey, these people did something. So it was very stressful, I can say, but it was just an experience in science that I always like to highlight. Science is not. Sometimes you read in the news like scientists say this and that. I mean, yes, we say this and that, and when it's really new, I mean, there is some uncertainty. I mean, and we hope that the community sees it, and as we progress, things settle down, and they become like more facts, right? And even the facts are usually correct, but that doesn't always prove the theories that we have put forward, right? It proves the fact that certain experiments can actually match the theory, but that never really prove a theory, right? We always are trying to disprove theories. We can disprove theories, but we cannot prove them, right? And so it's part of the game, and it was very stressful. And I say that this is my mistake that I remember, but it's actually, yes, it was a good experience. I was a postdoc at the time. Yes.
No, that's stressful. I mean, you're stressful. A major contributor.
Yes.
Cuddle Puppy says publication sounds so much better than publication. Is that an accent? Say publication? How do you pronounce it?
Publication, yeah, maybe publication.
Publication
I think in Spanish it's publicación. So it's like a stronger U.
Yeah, so publication versus publication.
Good ear, yes.
Good on you, Cuddle Puppy. So along those lines, is there anything accent-wise you've noticed that's been problematic in terms of like teaching class or?
Oh well, I do have a story about this.
I was gonna say, because in French, like happiness is happiness.
Okay.
What's your
well, actually, I was once in a conference shortly after the discovery of the Higgs boson, and the main talk was given by a French person, and the French person would talk about the Higgs. And I just say, okay, I know that it's difficult. I know that it's not native, but okay, this major thing you should be able to say Higgs. Okay, maybe that was my bad. But language-wise, for myself, so English is not my native language, and I'm sure that I still do a lot of mistakes, like is being cut. But when I was a student, one of the things I was studying was a process relating a particle that is called the Z boson. And as a Spanish speaker, the Z, the sound is very odd because we say theta. The Z is a theta.
Yeah.
So I as me trying to speak English, I would say the C boson. But of course, a native speaker is thinking of C like a cat, right? C, right? And this was really funny because it took me a while to actually correct it and say Z. Somebody told me, why don't you do it like the Canadian, because they say Z.
Z, yeah.
But I resisted, and finally I got it right to say Z. And I think the Z boson, which is, by the way, is one of the mediators. It's like the photon of the weak nuclear forces. It's a really important particle in the standard model of particle physics. Yes.
All right, so you've been grinding Donkey Kong for a while.
Yeah,
you got close.
Something.
You haven't beaten the first level.
Yeah,
I think you should.
But
I think you have to.
I can try. Okay. I can try.
Let's do it.
Let me just try to concentrate a little bit. Yes.
Yep.
The drinking is not helping.
It helps to some. So it's performance enhancing to like one drink, and then after that it goes downhill. Because I speedrun a bunch of video games, right? I try to beat them as fast as possible. And like one drink will relieve some of the stress. Like it is performance enhancing, but then you lose skill at some point. And I'm there because we're like 2 tequila glasses in and beer. Right. So, man. How's the joystick? How are you feeling about the it's a bit of a...
No, it's actually not bad. It's really good, and let's say it's very wide, right? So then that makes it that you can do very fine movement.
All right, we probably have, I don't know, 5-10 minutes before we'll switch over to NARC. I'm gonna run and bring some drinks into the kitchen. Let's do this one. What's your airplane conversation like? So when I go on an airplane and they're like, what do you do? I'm like, I'm a professor of chemistry, and they say I hated chemistry. So when you say I'm a physicist, in particular high energy particle physics, what does that conversation look like? How does that expand?
It's kind of a dichotomy in a sense, because sometimes people have the same reaction, like I hated it. I can finish. But there is also the reaction that people really seem to interested in different aspects of fundamental physics, right? People would say, okay, I'm really interested like in gravitational interactions or in cosmology, what is the fate of the universe, or for example, like the elementary particles, and of course the Higgs boson. I mean, is something that is in the news, and people normally remembers the phrasing of the God particle. So for the Higgs boson, there is a very famous book called The God Particle, which let me see if I remember the writer. The God Particle by forgot now. It's very, very famous physicist, but I escaped my mind at the moment. And so because there is a connection there with God and religion, perhaps. I mean, people actually caught up this when in 2012 we actually found the so-called God particle, but we don't refer to it as the God particle. We refer to it as the Higgs boson. So people actually know, and that's a typical thing, right? Like it's very, very interesting, and I'm happy to talk to people about what I do. It is interesting because it's very difficult to get to the point where I actually can describe the details of what I do. I mean, there's a difference between the type of goals of the things that I want to understand. I want to understand how particles interact and nature, but in the day-to-day, it's just like these very technical things about quantum field theories and computations. But in any case, it actually eases some conversation. I was just saying before that it is like this. People might say, yes, oh, I hated physics. I suffered through it when I was doing my study for, I don't know, medical sciences or something like that. But I also find a lot of people that even though that they are not trained in the technical sciences, they might say, okay, I'm really interested, and I have heard and I read a lot about it. Yeah.
Mm-hmm. Yeah. Cuddle Puppy says, this sounds like a very complex airplane conversation. I mean, it sounds like I came in when you were talking about, you know, the quote attributed to Einstein. Correct, if you can't explain it to a 5-year-old, you don't understand it, right? Can you
that's Feynman, maybe. Feynman, yes.
Was it Feynman?
Feynman was to his grandmother.
To his grandmother,
yes. Yeah. But yes, by the way, in my airplane, I often will be sitting with my computer doing something. Mariana, my wife, she usually says that I'm really good at this. I could be in a transatlantic flight and spend the night.
Oh man!
Just on it, like very focused, because perhaps the noise in the airplane, I mean, helps me with it. Yeah. And people would find that like crazy. Like, well, how can you do that?
I don't know. My new favorite thing is noise canceling headphones. Like, just cover your ears and you're just zoned in, and nobody tries to talk to you.
Yeah, that helps a lot. Yes, but I have a hard time sometimes holding to earphones. I just bothers me. So, and I don't mind the noise in the background. Yes, yeah.
All right, so we're at 10:30s, ladies and gentlemen. It's been 2.5 hours. Yeah, time flies when you're having fun, but it is time to transition to NARC. So, Fernando, we didn't talk about this much, but NARC is a game we make every guest play.
Okay.
And so it is a bargain bin game for the Nintendo Entertainment System. Okay. And so the thing about this game is it is not great, but it's also a fun thing for our guests to compete against each other. Mean? I will explain. Okay, you will learn the lore, but the thing about this game is we make every guest do this game, and we also make every guest race in this game.
Okay.
And so we have it set up so you have infinite lives, infinite rockets, infinite bullets, And you're going to beat this game tonight. It's a question of how long it's going to take you.
Nice.
And so we have a
rocks.
timer. Do you want to see the timer or do you not want to see the timer?
It's okay. I don't mind.
All right, so we have a timer right there, and we have NARC. So before you press start on this game, we're going to transition, ladies and gentlemen. It is time for NARC. We're going to throw up the NARC emotes. We have a couple of them, actually. But yeah, NARC is the game we make all our colleagues race to, and you can see that poster over there is everyone racing against each other.
Who is the top?
The top one right now. Let me look it up.
That's a good question.
And who do you want to know the numbers to? Because I have a bunch of your colleagues in physics and
That's
chemistry
true.
and
Maybe Rachel.
Rachel Yohe. Let's see.
I know that I also had Ted Colbert.
Ted Colbert was on. I've had Take's been on. Yeah. David Collins, Maya Murphy, Hanwei Gao.
Exactly. That's a lot of people you have had.
Yeah, physics. I have pretty good ties to physics, actually. Nope, that's not the
Let's
right
see.
one. I need to find the scoreboard.
So how's the score? Is like points or?
No,
Time
we're
or-
time. You want to do it in
time.
the shortest amount of time. So
Okay.
let's look it up.
And you only have one chance.
Yep, you have
Okay,
one.
yeah, I see.
Well,
I
your
have
first
to
time
learn
on.
about NARC.
When you come back again, then you'll know what's going on.
Okay.
So let's take a look. So I haven't completely updated the list. Here you guys can see.
I'm sure you have had way more experience.
All right, so here's the updated list. So
psychology.
Adam Dewan, he did 16:18, but we've had faster times
Is that
since
seconds
then.
or minutes?
That's minutes.
Okay,
So
minutes.
Tommy Usek did 12:14,
Nice.
and then our
Oh,
most
Tommy, I
recent
know
guest,
Tommy. Yes, yeah.
Jack
he's-
Justice from philosophy. He's just philosophy of
Nice.
science, actually.
Yeah, it
philosophy
seems
of
like they are
ecology.
leading.
Yeah, and so we have a couple 15 minutes.
It's like
So who do you want
philosophy
to know?
and
Rachel 24:32.
24, very good.
That's not bad.
Ted Colbert.
Ted, where's Ted on this? He's pretty high up. So-
There he is.
So Hanwei,
there is a 2.
16:26.
Oh, wow, good.
So that's pretty solid.
Hanwei, wow, Hanwei is really good.
Yeah, Ted 1922. That was the second time on, so that's kind of
Good.
cheating.
Christian.
Christian, Cyprian, 20
Okay, and
minutes.
Cyprian, very good.
Bargov, I don't know if you know him from math. He does
I
like
don't know.
biomathematics.
Okay.
Who
Nice.
else?
You have
Ted again.
is added number 1 is.
2022.
Very good.
Yeah.
So what is the aim? And
David
David,
Collins.
okay.
I mean, if you get it in 25 minutes, you're doing well. So
Very good.
there's the scoreboard, ladies and gentlemen. And knees weak, arms
What
are
about
heavy.
Nathan? Nathan, do you have Nathan there?
There's Nathan, 1722.
Oh, wow, he
he's
did
pretty
amazing.
solid. So he's top 10.
Wow.
And Nathan's a gamer. Like there's
Oh, yeah,
no
yeah,
question.
yeah,
Nathan
probably.
actually games.
I don't know if I didn't know this, but it doesn't surprise me in a sense.
All right, so we're going to close that up. We got NARC on the screen, and I'm going to give you the backstory so you know what game you're getting into. So here's the cartridge, the original
Okay.
Nintendo cartridge. All right, ladies and gentlemen, NARC, no one had the guts until now. You are Max Force. Your mission, bust Mr. Big and destroy his dreaded criminal empire. Seize all contraband, stolen money, illegal weapons, use rocket bombs, high-powered machine guns, apprehend all suspects, protect the innocent, punish the guilty, stop at nothing. So that's NARC. So you're gonna win the
Sounds
war
like
on
a
drugs
very important
tonight.
mission.
Yeah, exactly. No, we're gonna win the war on drugs tonight. And so I'll just give you a brief overview. Like, there's no advantage in killing anyone. You just
Is
want to
it
walk
with this,
right.
by the way?
It's gonna be with the Nintendo
with the
controller.
Nintendo.
And so you're gonna walk right as fast as you can. Jump over bullets. It's not an advantage to turn back and kill anyone.
Okay.
Go find doors, and you're gonna go through them. I'll walk you through as we go through. But
I didn't ask an important question.
what's the important question? Let's do it.
Who has been the slowest?
The slowest. Oh no, let's take a look.
Because I might be that one.
And so there's
after
a
this game.
terrible boss fight at the end that's a jump rocket, and it's actually really hard to do.
Okay.
And so anytime somebody has an asterisk next to their name, it means I intervened on that boss fight.
Okay. So maybe I will be one of those.
So we're upwards of
I see.
40 minutes on some of
Good.
them.
I see some of the names there. Let's not name names.
Yeah, exactly. All right, so
But I will be there.
I'm gonna put up the timer quick on the screen so everyone gets to see it.
Okay.
There's live split. Come on, give me that. There we go. All right, you guys can see the clock.
So what do the
right.
buttons do? And
All right, so
I
I'm going
move
to
with
walk you
these,
through
or-
it. You're going to press right from the start. So go ahead and press start button.
start.
And then as soon as you hit the ground running, just press right, and you're going to walk to the right.
Right. Okay.
And then I'll tell you what the other buttons do.
Okay.
All right, clock is going. there's your timer. Oh, so if you tap B, it's a jump. If you hold B, it's a squat. So tap it like staccato, very like gentle.
B,
so B, tap it lighter. Go through that door right there. Keep going right. So tap B. You want to get to jump. So you're pressing it too long and too hard. So yeah, there you go. So it's 7 frames. So 7 sixtieths of a second.
I mean, but if I press B, it does.
So don't press it too hard. Just like it does. Yeah, there you go. Not all the way down. So yeah, very
There's
like.
a dog. It's fighting me.
Exactly. So very like staccato is the best descriptor I can give to somebody that knows music. Like it's just a very gentle.
Okay.
And then if you hold A, it does bullets. So hold it down. If you tap A, it's a rocket. So less tap. Touch that safe card, go through that door. First level's done.
Oh, okay.
All right. So you're gonna want to practice that tapping B,
And
tapping A.
the other guys were shooting at me. Right?
Yep. So those are the drug dealers that are trying to inhibit you from whatever your goal is.
So now it's again the same.
Yep, go right. You're gonna have different people. In this case, you're gonna have people like shooting syringes at you. And so I would practice the tapping B and tapping A, because there's a boss at the end, and we didn't get to practice because we were setting up the quest. This is literally the first time Fernando has ever seen this game. So most of the guests get a couple minutes of practice. We were troubleshooting a connection and stream of the quest. So yeah, tap B and then tap A in the air.
Tap B, but okay.
Yep, and then in the air you're gonna do
it. It's very sensitive.
Yep, exactly. And so it's literally, if you do it under 7 frames, you get a jump. If it's 8 frames, you don't do anything, and then it's 9 frames, then you do the squat. So practicing that jump rocket. All right.
How many lives do I have?
You have infinite lives,
Oh,
infinite bullets,
lives.
infinite
Okay.
rockets. You
It's
will
all
beat this
about
game.
timing.
Yeah,
Okay.
exactly. So what you're gonna do
excellent.
here, you're gonna shoot the guys wearing black with bullets. So hold the A button
Okay.
and shoot them. Yep. Hold A and shoot the guys wearing black. So basically kill everything on screen.
So
hold A.
I'm trying to
So
go exit,
one of them
I
is going to
cannot.
drop a blue card. So shoot A, hold A to shoot them. Hold A. Yep, hold it down. Yep. So hold it. Yeah, you don't have to tap it. Just literally hold the button A. There you go, blue card. Grab that blue
I
card
have to- okay.
and then go through the door. Well,
How do I
just walk over it with Nintendo's shitty hitboxes.
I have to get
Walk
the
over the middle. Yep, that safe card. There you
Oh,
go.
there you
All right, put it in the slot. Go out, and then through the door. So to the right, put it in the slot.
Oh, I have to put it in.
Yeah, no, this is realistic.
Okay. I see. Okay, good.
All right. Leo's Fermi, welcome back to the stream. Thank you for joining us. They're asking, what's your experiment? What faculty are you? And so our guest today is Fernando Febres Cordero.
Yes.
Right? How do you pronounce it? What's the
Febres
actual?
Cordero. Well, if in Spanish, or Febres Cordero.
Cordero. Okay. And so Fernando's a member of the Department of Physics, and so he's a high-energy particle physicist. What experiments does he do? He does in silico experiments. So walk right.
That's right.
Yeah, he doesn't actually do experiments in terms of the traditional like lab-based experiments. He's a theoretician that does models of systems and then compares the models to experimental data. So yeah, if you have any questions about high-energy particle physics, particles, how the particles interact, how the particles or how current models relate to tap B to jump and get in the car. So gentle on that B, a little less on the, yeah, there you go, go right.
Oh, nice.
You're gonna run into a bomb at some point, and that's okay. Just keep going. There you go, keep going right. And so if you guys have any questions for Fernando, he's happy to answer those while he tries to win the war on drugs. So that's what we're doing at the closing of the night. No pressure.
I think 30 minutes will be good.
Exactly. I mean, sure, the U.S. government has spent $3 trillion on this, but we can beat it in one game.
But that guy is blue, so maybe he's good.
No, he's Joe Rockhead. He's trying to kill you.
Oh, okay. So I should be fighting.
Yeah, they're all bad guys. There's no even the dogs. Even the dogs
All
are
are
bad.
bad.
And so press jump to get over this. And what I recommend is practice the jump. So make sure you can hit that jump, and then while you're in the air, shoot a rocket. So like when you're at peak, then tap A. Yeah, there you go. That's pretty close. A little gentler on the A button.
Nice.
And so you got to
And
do
I
it.
have infinite.
Yeah, you can
grenades.
practice this indefinitely. Yep. And you might as well, because this is a long walk across the bridge. But yeah, if you guys have any questions for Fernando, he's happy to answer those while he wins the war on drugs. Again, experimental theoretical particle physics, he's happy to answer those. My question for you, and we asked this of all our particle physicists, Ted, Rachel, what's your favorite particle?
Oh, my favorite particle. Good question. Well, just think about it before I answer. I should keep going.
Yep.
What
Yep.
about this?
You can
duck?
press both buttons down, and you can squat shoot.
Okay.
So press both of them, and then turn
Nice.
and shoot the dog. Yeah.
Nice.
And keep going right. It slows you down, so you don't want to do it the whole time.
So there is a particle that I actually
Stay on the bottom.
was able.
Go up to the
Ooh,
top.
nice.
Go up. All right. Keep going. You're gonna hit a wall. Keep going. Jump and keep going.
I was able to predict something new. It's the W boson.
Oh, really?
Something that was not known before, and one of those things that you sort of come across by a little bit of luck, serendipity, you can say. So maybe the W boson. I really like him. I mean, we actually predicted that the W boson is produced in a very odd way, and this has been actually measured. So yes, maybe I can say that one.
That's awesome.
But of course, I
it's
mean,
one that you were involved in the discovery of. That's amazing.
No. The discovery happened when I was like a baby. But the
So stay on the bottom all the way to the end.
But the property was actually what I predicted. But definitely because of the time in which I have been doing physics.
Jump.
Oh, I have to jump. The Higgs boson is probably
Tap
the
it.
most interesting.
Oh, you don't have to run. Just
and
stay
actually,
close.
and actually, the Higgs
Stay next to it. Yeah, there you go.
The Higgs boson is like the very odd guy in life, yes. Why? Because it's the only particle that is scalar, but to go to the sex.
Yep.
Oh, there you
To the nightclub. That's fun.
Yes.
Leon
but yes,
says-
let's say the W. Yeah.
W is weird. It's the only comment in
It's weird.
chat.
He's only left-handed. Actually, it is.
I mean, handedness is such a weird phenomenon.
Yeah.
We have this
but in chemistry, it's beautiful, right?
It is beautiful, but it's also weird. Why is our existence dependent on
Yeah,
handedness,
exactly.
right?
Yeah,
And
it makes a very big difference. I mean, physicists were very surprised when they realized that the universe was not symmetric on their handedness.
Yeah.
That left-handed and right-handed.
And there's a preference to like celestial rotations and
Correct.
black hole and directions and galaxies. Like, what a
Well,
crazy, weird thing.
yeah,
All right,
well-
grab that card. You're gonna
Oh, the
pick
safe.
that up. Yep.
So I have to press something. Or...
No, you just have to walk over it. There you go.
there you
And
go.
you're gonna go through the door, but don't press up after you go through the door. So go through the door. Nope. Then you went back in. So that's
Oh, I went back
yeah.
in.
So go to the right, find the last door, and then you'll go up through it.
Again. Okay. So this game was played by people, like, seriously?
What depends what you mean by seriously. Cuddle Puppy, do you want to reveal it? Should I?
So do I now what?
Go left. You see
Left?
that
Okay,
silver
now it's
card
left.
slot? You're gonna put the card in there and then walk through that
I
door.
see.
And then that's the level.
Very good. I remember a friend of mine showing me maybe like 15 years ago this video game, this YouTube video that was that's very difficult.
Yeah, go right.
Yeah.
Find a door. After you go through the door, this is the only level you're gonna go left.
This is the only level we go left.
Yep.
Okay.
So go through that door.
Oh.
Go up through that
there
door,
he is.
and then left. And you're gonna shoot these Rambo-looking guys with bullets, but at kind of close range. So not at the end of the screen. So don't shoot them there.
Okay.
Let them get closer. And go up a little higher because they're gonna have to drop a green card. So kill that guy to the right. Shoot him. Bullets.
Do I need to exit to here?
You need to shoot him to have him drop a
Oh,
green
I see.
card.
Oh, this guy.
And the problem is that further research only gets more complicated and expensive. That is the extent of human achievement, actually. Experiments used to be very easy and very simple, that people did them on their own budgets in their own households. And yeah, we've only progressed since there. So it's going to be a green card. So kill that guy, then you'll kill him again, and then turn around the other way, kill that guy. Eventually that guy, Rambo-looking guy, is going to drop a green card.
Oh, I see. Okay, so I have to keep killing people.
All right.
Oh, there you go.
Yeah, there
the
you go.
save.
Pick that up, then you put that in the door. And so your question about do people take this game seriously? And the answer is only a few people. And one of those people is me. And so it started out as a joke because I played this as a kid and I was the guest on the stream once, so I played it. And then I started making every guest play it.
Okay.
And then the stream challenged me to do this as a speed run, beat it as fast as I could. And what I did is I figured out a way to beat the boss faster. And for a 6-month period, I was the world record holder in the speed run of this game.
Wow.
And so that's why I make every guest play it. And so yeah, a few of us take it seriously, and there's a YouTube tutorial on how to beat this as fast as possible by yours truly. So next time you're on, if you want to learn it, you can beat this
famous.
game. Yeah, exactly. Literally dozens of viewers.
I thought that the cars wouldn't go through the sidewalk, but they do.
Yeah, no, they'll go anywhere. So if you go up or down. All right, Leoz wants to know, don't know whether this is proper theory, but I'd like to know, has there been any develops on axons recently?
Actions.
Axions. Okay, so axons is the length of a neuron, but axion is a particle in physics, right?
So definitely, I mean, those are one of the. So the actions first appear as a solution to a problem that is called as the strong CP problem, and wow, this is very
Keep going
busy.
right. Keep
very
going right.
busy. Lots of people.
No, that's good.
So the strong CP problem is like one of the. So the standard model. I was making a joke about ChatGPT and having like red card. Okay.
Yep, you got the cards for the next
About
one.
ChatGPT having 1 trillion parameters and being able to do anything, to fit anything. So in the standard model there is 19 parameters. One of those parameters is a very tricky one. It's about the structure of the vacuum of the standard model, and that parameter has a very funny value. It has a value of like 10 to the minus 10. It's very tiny, and let's say you would naturally think about it as like being order 1. So, but then there is a procedure, a dynamical model that produces these very small values, and it produces a particle that is called the axion. And so originally people were looking for it for a long time. So up until now, this is just like a theory, and there is a lot of different situations in which actions can appear. But up until now, yes, it's just theoretical. There is no proof or anything.
So hold both buttons, you can shoot the dogs.
They don't. Okay. Such that they don't eat.
Yep, hold them, turn around. Yep. Turn around, you can get them. Yep, keep going right. Don't hold them while you walk right. Yeah, there you go. And when they're back, hold them both. They turn into puppies. Now walk right. Let go. Yeah, there you go.
Yes. So yes. Up until now, yes. No evidence that these particles are actually there. Or not.
Oh, interesting. It's just a theoretical particle right now. Is there an experiment that would definitively show?
No, because the parameter space associated to them is rather large. So let's say experiments that are running could potentially show that. Do I have the card now? Or?
You do not. So you got to kill everyone on screen, and the wheelchair guy's going to appear. You're going to shoot rockets at him. So tapping A when he's on the screen. So tap a whole lot of A. Gentler. Yep, there you go. Just do that over and over again. There you go.
Oh.
One time. You need to do that twice more.
So it's very difficult to kill it, meaning like to prove that it doesn't exist. But it indeed is being searched in many places. It just has not been found yet.
All right, Ostray Cat, welcome to the stream. Thank you for joining us. First time chat. If you're not following, you should click the follow button along with anyone else that's here for the first time. Follow us. We love having those. Also, you get notifications about future streams. We have a guest every other 2 weeks. With that said, it'll be a couple weeks before we have another one. But nonetheless, Ostray Cat 7 wants to know, Dr. Hansen, are you a cat or a dog person? This is a very important question. Oh man, I will answer honestly, regardless of the consequences, but I am a cat person. And it's mainly because of the independence of cats, like the scheduling commitment of a dog, right?
Yeah.
Like you have to let them out certain times a day. Cats are mostly self-sustaining. As long as you have a clean litter box and some food, they are perfectly fine. Cuddle Puppy has decided to unfollow us.
But I'm a dog person.
You're a dog person,
yeah,
all right.
Definitely.
It
we have a
equals
little dog. I mean, little. She's really big. We call her Shats. Her name is Shats, and we love her. Yes, but it's true that you need to dedicate a lot of time
It's
to
the scheduling commitment.
Yeah.
Really.
And, but we love her. Yes.
All right, tap A. You're gonna get a rocket. A little gentler. Oh, that was close. There you go. All right. So he's gonna dissolve into a gold card, and then you're gonna pick up the gold card, and you're done with phase 1 of Mr. Big. All right. Leo Oz wants to know, we found the Higgs. So what's the next big gaping hole now?
So, yes.
So pick up that card.
Yeah, I'm trying.
Sorry. All right. Nice.
Okay.
All right. Then you're through the door.
So yes, the standard model was the last missing piece for the last decade, because the Higgs was found in 2012. We have been trying to actually settle whether the thing that we found is actually what we expected.
All right, I'm going to intervene quickly, so go to the top of the screen. What you have to do is do a jump rocket into the hat.
Oh,
and so you want to be at the very top of the screen so his tongues don't hit you. Okay. Those are his tongues.
Okay.
It's the war on drugs.
so I have to jump and throw?
Yep, so get away from him, run to the right or left, jump, go to the top of the screen, go higher up. Because if he's hitting you with his tongues, you're not at the top of the screen. So press up more, up further, like just literally the up button. All right. All right, so now you're going to pause or stop and then turn back and then jump rocket him. So that's the hard part. This is the great equalizer. You have to jump and hit him in the hat.
So I have to jump?
Yep. So tap A and then tap B. Or tap B and then tap A, I apologize. So go to the right, get away from him a little bit. Let's just walk right. Get some distance, further than that. Because once he gets on you, you're in trouble. Because you're going to, just get destroyed. All right, now jump rocket. And you don't have to go towards him when you do the rocket. So run away to the right. Like, get him off screen. And then just turn around and look back. Stand still, jump rocket.
Oops.
So yeah, you can go the other way and get a bunch of distance. This shows you where you are on the screen.
I see.
And this is the great equalizer. This is the one that...
So I have to, again, look towards him, and then...
You don't have to walk towards him. Stand still.
And then
stop moving. Yep. So go that way again. So,
I don't have to walk towards
No, you don't. You don't. So get a good distance and just stop moving, turn back, jump rocket. So tap B and then A on the way. That was very close. Tap on A and you'll get a rocket. So run to the left and you can do that again.
Okay, I see.
And if you get this one, this is the hardest part. This literally is the hardest part. Unfollowed because I like cats. It's just the inconvenience of dogs. Either of you visited CERN much? I have never visited CERN. Have you gone there?
Yeah, sure. Many times.
And is that for fun or is that like value and
for
experiment?
both things. I mean, I think I have visited for just like with friends, but mostly it's because of work. So there is
like
a
it's
lot
a conference or meeting or something.
Exactly, conference meetings, all kinds of workshops. So I jump.
Oh, that was very close. Yep. So on the way down, you're going to tap the A button. So run that way and do it again. And you were very close on that one. So if you're just gentler on the A tap. So really quick B. Yep, a little later on the A. It's a very gentle rhythm. If we had a music note, I don't know. I should write this out in like
in
yeah, like a full versus a half.
let's see.
And then it's got to be staccato. There it is. Now rockets to the face. So no more jumping, just rockets. So get some distance from him, run away. He's gonna kill you. It's fine. Take those iframes, run away. So get some distance. Now you don't have to jump anymore. Just rocket him in the face. So he's gonna come out. Rockets. There you go. Okay. So now you're gonna run away from him and get between these two black lines. And so now with no more rockets, it's just gonna be bullets.
Between the two black.
Yep. So down here between those two black lines. And so it's going to be holding A from now on. So get some distance. So get a little further. Yeah, get away from him that way. And then once he's off screen, turn around and shoot. You don't have to run towards him. Yep, and then go away. And then go back. You got one of them. You saw the points that popped up? There's another one. So go back that way. And you're going to turn around and shoot. And if you move up and down, it typically helps. Just like a little bit of jiggle up and down. There you go. Do that and go. That's another one. All right, we're making progress. So Rachel and Ted regularly visit CERN, right? They go like every year.
Of course, because they do.
They're
work
experimentalists,
there.
right? They design it.
That's a different thing.
Mm-hmm.
I mean, they
Oh, there you go. All right, go right. That's excellent time.
Very good. No. I go there as a theorist, and of course I'm very interested in the experimental results, but I don't go for actually doing like shift work or working on the hardware, which they actually do.
Yeah. And so yeah, you're gonna go to the right. If you guys have suggestions on someone we should raid, put those in now, because we are almost done with the stream. We have about 3 minutes left. So Fernando, this is it. You are on the this is the civil forfeiture of the level. You've beaten the drug lord. Now you're stealing all his gold.
Yeah, I am. That's the all of the gold. Okay.
There it is. 21:31.
21, not bad.
That's solid.
Not bad, yes.
Not the best, not the worst. You're top 50 for sure. I mean, there you go. Congratulations, you've completed the NARC training mission.
Very good.
Nice work.
I feel accomplished.
Contact your local DEA agent.
One of my good memories.
Oh
like
no,
this.
this needs to go. This has to go on the resume. 21:31 in NARC is no joke. You did it, and especially you got 0 practice time.
Yeah,
You jumped into this cold. I really respect that.
But that guy with the hat, that was difficult.
Yeah. So now you get to put your initials in. You only get 3 of them because classic arcade. All right. I mean, it looks like we got the Higgs, but now, what would we do now? What's the next big thing? Well, what are you excited to see out of experiments that's going to change the way you think about the world?
Yes. So, I mean, we have all kinds of questions because, as I said, there is this disconnect between how good our models work in the lab and how bad they actually look when we look at the astrophysics. And so we would first wish to explore yet a different range in energy, and for that we hope to have like a more energetic collider. So it's just that these are very expensive exercises. I mean, it's not like something you do out of a hat, right? I mean, it takes a lot of effort, a lot of time. So I don't know if we are gonna get a collider anytime soon after the Large Hadron Collider.
But they're upgrading a bunch of detectors at the Large Hadron. Right?
We will have the high luminosity LHC, and this will start. I mean, there is a lot of work being done related to that at FSU, in particular through groups like Rachel's and Ted's. So it's very exciting, and that's gonna bring us into a new era of precision. But a new collider, like a new energy regime and larger tunnels, I mean, this is still open question. There is this idea that the US is trying to push of a muon collider. Muons are these particles that they look very much like cousins of the electrons, the heavier ones, but they decay really, really rapidly. And so maybe in the US they will be able to build one of these colliders, and that's very exciting because there are several technical features that we can achieve there that we are not able to do it in a hadron collider. So that will be very exciting.
other than that, well, I mean, so we keep finding ways of testing the standard model, and if it breaks at some point, I would be. It's kind of funny because I dedicate my life to learn about the standard model, but I will be so happy if we finally find the breaking point. The thing has survived 3 decades, 4 decades, 5 decades, and we would really like to see it explicitly failing, because the moment it fails, we try to dig in and see where is it that it happens and what that teaches about nature, and that is very exciting. It would be very exciting.
So I served on one of Ted's students' committees, and then they brought up this metric when analyzing the standard model, and it's I don't remember the Greek. It's like theta. It's the fraction of wrongness of the standard model.
Yeah.
And my question, exactly. And it was like they have like experimental versus theoretical, or theoretical versus experimental.
How far away there?
Exactly. And the answer wasn't 1. It was like converging on 1.2 plus or minus 0.2. So it might be wrong completely.
Yeah, maybe.
And so my question was, if it is wrong that direction, what parameter is making it wrong in that direction? And
so that when that settles, and we have significant statistical evidence that this thing is breaking, because fluctuations, they happen all the time, right? I mean, you measure things and they fluctuate around the expected value, let's say, but if these fluctuations become so statistically unthinkable, I mean, like it's like a random fluctuation, then we will start digging deeper and try to understand what is it that is causing this, and hopefully we can connect it to these long-standing problems like dark matter and dark energy. We will see. There is another interesting problem in the universe, which is that there is a lot of matter and not so much so antimatter, and that's one of the also problems of the standard model, because we wouldn't expect that.
Mass balance. We need mass balance. It doesn't make sense without it.
Yes.
That's awesome. So thank you, Lee Oz, for the question. We really appreciate it. All right, Fernando, that's it. We're done.
Thanks a lot. It was a lot of fun to be here and play some games. Sorry that I'm so bad, but I tried.
Of the spectrum of guests, 2131 is a solid standard. I mean, you were very hesitant coming into it, but 3 hours later, how are you feeling? You're content? You're
I'm very happy. I'm very happy. Thanks for having me, and hopefully I can play more video games.
I'm really glad the Quest worked out. Like the VR.
That was actually really awesome. I mean, I wasn't given too much chance for it to happen smoothly, and it kind of did it smoothly.
I mean, we troubleshot. We got it going. So I really appreciate it. Thank you very much, and thank you for saying yes. Especially last week of class is very busy time for everyone. I really appreciate it. Hopefully you guys have a good time. Those of you that are students are still studying. Hopefully your finals go well. But yeah, it's been an awesome time, Fernando. Thank you again very much for
thanks for having me. And
any parting words for the audience? If you had to convey information to the world, if you had the voice of a microphone that goes across the world and you want to convey it about your field, what would you say?
I don't know. Keep being, like creative and curious about things. Yes, I mean that's what's always fun. Yes,
that's a very good start.
Challenge your thoughts. So yes.
Exactly. Yes. Trust nothing. Standard model's probably wrong. The next model will probably be wrong.
Yeah, exactly.
We are indefinitely wrong. We'll die
layers
wrong.
Of the onion.
Exactly. We peel it away. All right. Thank you all for joining us. It's been a lot of fun. We've really enjoyed this evening. It's been awesome. Stick around. We're going to raid someone educational related. There's a few streamers that come out on Wednesday night. We're at an unusual time. But nonetheless, our next guest, I'm going to put it up there, is I have no idea who it is. And so Rashida Harbaugh was supposed to be our guest. She's a developmental psychologist / neurobiologist that studies like development and child learning and things like that. She had something come up, so she can't be the guest on December 17th. So we don't have anyone lined up. Worst case scenario, if I don't find a guest, what I'm going to do is ask Eugene DePrince, my colleague in chemistry. We're going to do some speed runs in NARC. And so I had the former world record in single player. Eugene has committed to doing the 2-player world record in this particular game. And so 2 weeks from now, if you guys are interested, Eugene and I are probably going to try to do a speedrun world record in NARC. So we'll hang out in December. Yeah, he'll be on the stream. It'll be interesting. What I like about video gaming and speedrunning in particular is because it's just an awesome exercise in scientific method. right? Because the rules in the game are very different than the rules in reality. And so you spend your time learning the rules and then exploiting those rules to make your speed run faster. And so it's a really fun exercise in scientific education. Nonetheless, yeah, we won't talk too much science. We will be speed running probably in 2 weeks, because who wants to join us right before the holiday break? Nonetheless, yeah, exactly. But I will line up a spring schedule. I'm reaching out to people now. I'll probably post that sometimes at the end of December, and you guys will see. We'll try to do every 2 weeks. It's going to be a little messy because I have some travels in there, but we will have another lineup of 7 or 8 guests between January and May. And so keep your eyes on that. Follow us if you're not following. You'll get notifications. Also, check our About Us tab. We'll have a schedule listed of the individuals, or follow our Discord. That's shown up in chat a bunch. So yeah, TBD is also my favorite scientist, Cuddle Puppy. Thank you. I should put Dr. TBD. But anyway.
Professor.
Exactly. Professor Doctor. We're doing the German route. They've earned their title. Show some respect for TBD. All right. But everyone, thank you for joining us. Thank you for following. Stick around. We're going to rate an educational streamer. I think, yeah, let's go after some astrobiology here. But ladies and gentlemen, it's always a pleasure. Fernando, thank you again. It's been awesome. All right. We'll see you guys in 2 weeks.